Good morning and welcome to day 6 of the AMALathon. So we're on our final day. Thank you for those that have been the whole way through. Thank you for those that are watching it as a recording. So as I mentioned yesterday, this was a triple topic, and thank you to those that have managed to get on at 9:45. Now we've not got too much to complete today, but we are going to keep going through it till it's finished. So as you guys know, biology is done. So we're going to finish off this titration bit. Then from the rest of topic 4, we're going to be finishing off electrolysis. Then we're looking through topic 5. The end part of topic 5 is triple, but we're going to go through that in sequence, not at the end. Then we're going to finish with the last part of atomic structure. So once we finish topic 5 chemistry, then it'll just be triple award topics after that point. Okay, so let's get started. Now there is a really nice question that this topic finishes with. And like I've said, for any practical work, my advice is really simple. Watch the videos. There's only so much theory you can do. You need to see it actually physically, and you need to be able to see what actually happens. So you can understand how the apparatus interact with each other. There's only so much that I can do from a theoretical perspective. I'm sure you've done it in school, so you already can visualize everything. Now, what can titrations be used for? So it helps us find out the concentration of acids and alkalis. So the concentration of acids and alkalis can be analyzed using titrations. During the reaction, hydrogen ions from the acid react with hydroxide ions from the alkali to make water. So neutralization occurs. An indicator is used to determine the point of neutralization. So it's possible when you did this experiment, what you added in here was an indicator called phenolphthalein, which is initially colorless. And then as you add more and more alkali to it, the second it becomes an alkaline, so the second it goes from being an acid to being alkaline, it becomes a pink color. And initially you would have seen you would have added, and when you do this experiment, initially you add in 1 centimeter cubed at a time, then right at the end you start adding it dropwise. And you get to a point where each drop you see that change of you see that tinge of pink coming through, until there's one drop where the whole thing turns pink. That one drop is the point where it goes from acid to alkali. So that's the neutralization point. So the whole point of titration is to find out the neutralization point. Once you've worked out the neutralization point, you can do the calculations to find out unknown concentrations. So let's go through the actual process. So initially we use a pipette, and a pipette is a very accurate instrument that helps you get exactly 25 centimeters cubed of a liquid. Or you get a pipette. There are pipettes which are accurate to 25 centimeters cubed, and that measures a known volume of alkali into the conical flask. Then you add a few drops of indicator, for example phenolphthalein, which is the most commonly used one, or methyl orange. Methyl orange starts as an orangey red color and it becomes yellow. Phenolphthalein starts as a white color and it becomes pink. Then you fill a burette with acid and record the starting volume. So your burette goes up to 50 centimeters cubed. Now you fill the burette with acid, record the starting volume, slowly add the acid from the burette into the alkali, swirling the flask. So it's quite a skill that you will definitely have to master if you're doing A-level chemistry, that you swirl whilst you add the acid dropwise. Then you stop adding the acid when the indicator changes color. Now before you get to that point, as soon as you get to a point where you can see the colors starting to change every time you put a little bit of acid in, that's the point where you add it in dropwise, 1 drop at a time, because it will literally be 1 drop that makes the color change. This is the neutralization point. Now then you record the final burette reading. and calculate the volume of acid used. Now you have to repeat the experiment until you get consistent. The correct word is concordant results. Concordant means that they're within 0.1 of each other. So 0.1 centimeters cubed of each other. Okay, let's go through some practice questions. A student is measuring how much sodium hydroxide solution need to react fully with 25 centimeters cubed of dilute sulfuric acid. So let's zoom into this so we can take the measurement. There we go. Now this burette, let me just get my pen back. In this burette it started at 0 and its endpoint is 50. So we're measuring downwards. Now when you measure this, you look at the meniscus of the water. So we're not measuring at this point here, we're measuring at that line just there. So let me just remove that now because I've drawn that quite thick. So if we look at what that line is there, it is at 27.5, 27.6. So let's check the answer. Zoom back out. Yep, 27.6. So when you read this, you have to check the meniscus, so which is the bottom of that curve. Because of the way water molecules bind to each other, so if you have a water molecule, another water molecule, you'll have weak intermolecular bonds. So that means the ones towards the top here that have bonded have got weak intermolecular bonds with the glass from the burette, they attach to the ones below, 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 so they pull up the water slightly at the side. Now when you get towards the middle, the force of gravity brings it lower down. So you're measuring this point here, not this additional amount of water at the side there. That's just that's just due to the cohesion or the weak intermolecular bonds between the water molecules. So let's have a look at the next question. The higher the concentration of a sample of dilute sulfuric acid, the greater the volume of sodium hydroxide needed to neutralize the acid. So the student tested two samples, P and Q. Describe how the student could use titrations to find the sample P or Q, to find which sample P or Q is more concentrated. So it's the same process we went through before. Measure the volume of acid, add an indicator, so add that to a conical flask, then add an indicator, add sodium hydroxide solution, as a measure volume of acid, let me start again. So yeah, add so when you measure the volume, in this case you're measuring the volume of acid, you're adding it to a conical flask, then you're adding the indicator to the conical flask, then you add your sodium hydroxide solution to a burette. Then you keep adding it till you get a colour change. Now just before you get to the end point, when the colour changes, you would add it dropwise. And you keep adding it dropwise till the colour changes. Record the volume that you've just added of sodium hydroxide. Then you would need to repeat that until you get concordant results. It doesn't mention it here, but you repeat with acid P until you get concordant results. Now, once you've got concordant results, you repeat the same process with acid Q. So you measure the volume of acid Q, you add an indicator, put all of that into a conical flask, you add your sodium hydroxide to a burette, and you add it until you see a colour change, and when you see the initial colour change, you now add it dropwise until it permanently changes colour. You record the volume and you repeat till you get concordant results. Now you've got concordant results for both, you can compare. Now the other things that you should have mentioned is when you're adding the acid, so when you're adding the sodium hydroxide to the acid, you should be swirling the conical flask. You should have a white tile underneath, and the reason we have a white tile underneath is so you can see the color change really clearly. We've already covered that. We have to repeat it till we get concordant results and take a mean. Concordant means results which are 0.1 centimeters cubed of each other. I'll make more sense in the next slide. And like I've already mentioned, you add it dropwise till when you get to the end point. So when you get close to the end point, the point where it's gonna suddenly change the indicator changes color, you add it dropwise at that point. Now I'm going to repeat that just one more time because this is a really good question to memorize. And just to reiterate what we're saying here, when you've got your burette like this, that's the meniscus. So that's like almost like the skin of the water. So if you ever put water in a glass, the water, if you keep adding water to it, it doesn't just stop at that line there. There's always a little bit over the top, and that's because of how water binds to each other. Even if you put a drop of water on a table, you'll notice it almost bubbles up like this, and that's because the bonds between the water molecules. As soon as you kind of poke it, the water spreads out, because you've broken the cohesion. So when you're measuring it, you look at the meniscus, and it's that bottom part of that curve that you're measuring. That's the part that tells you the reading. Okay, so here, the higher the concentration of a sample of dilute sulfuric acid, the greater the volume of sodium hydroxide needed to neutralize it. Now the student tested 2 samples of dilute sulfuric acid, P and Q. Describe how the student could use titrations to find if sample P is more concentrated or sample Q. So what you do is you take sample P initially, you measure the volume of sample P. So for example, it might be 25 centimeters cubed. You add it to your conical flask. Now you add an indicator so that it changes color. Now if you use phenolphthalein, it'll just be colorless. Then you add your sodium hydroxide to your burette, which you can add a maximum of 50 centimeters cubed. So usually the best thing is just to take it to 50 centimeters cubed. Then you start adding the sodium hydroxide. Now you initially can add sodium hydroxide 1 centimeter cubed at a time until you start to see some color change. At that point, you add it dropwise because you need endpoint. Endpoint being when it goes from acid to alkali. We want that exact drop when it's neutralized. When you're adding the sodium hydroxide, you've got to swirl it, and you've got to make sure you have a white tile underneath so you can see the color change clearly. Once you reach that color change, when it's permanently changes, that one drop that causes the color change, you record that volume, then you need to repeat and take a mean. But we continue to get concordant results, meaning when it's 0.1 centimeters cubed, where you've got 2 or 3 results which are within 0.1 centimeter cubed of each other. Then you take an average of those results, and you do the same thing with Q. So at that point you can see which one required more of the acid to neutralize. Which one required more sodium hydroxide to neutralize it. Okay, this is a fantastic question. After we've done this, we are going to move on to electrolysis. So anyone that's logged in for combined will become combined as soon as this question finishes. So we've got a student titrated 25 centimeters cubed. So here we've got a volume of 25 centimeters cubed. Now we want decimeters, so we divide that by 1,000. So it's going to be 0.025 decimeters cubed. And we've got a student tried to make 25 centimeter cubed portions of dilute sulfuric acid with a 0.105 moles per decimeter cube sodium hydroxide solution. So on the other side, so this is the information we've got about H2SO4. On the other side, let's write the information that we have regarding sodium hydroxide. So we know moles equal 0.105 moles per decimeter cubed. We also know the volume of sodium hydroxide. Now we've got 1, 2, 3, 4, 5 results. Now from these results, the only results we can use are the ones that are concordant. Now the concordant results, so because it says they use only the student's concordant results. I should have read the whole question first. The equation of the reaction is here. So 2 sodium hydroxides react with 1 H2SO4 molecule. We're calculating the concentration of sulfuric acid. Used only the student's concordant results. So the concordant results are these ones, 1, 2, and 3, because they're all 0.1 within each other, of each other, 0.1 of each other. So concordant results are those within 0.1 centimeters cubed of each other. So here, therefore, is our volume. So the volume of sodium hydroxide is 22.13. Because look what they've done, 22.1, 22.15, 20 plus 22, sorry, 22.15 and plus 22.15, add them all up and divide it by 3. We don't need this one because it's not concordant. We don't need that one because it's not concordant. Now, so we don't have moles here, we've got concentration. Now we can work out the number of moles of sodium hydroxide. Moles equals concentration times the volume. Now we want to convert this volume into decimeters. So that's going to be, we're going to have to divide it by 1,000. So the volume we're going to divide by 1,000, so it's 0.02213. So look, that's what we're doing here now. Moles of sodium hydroxide, it's 22.13 divided by 1,000. That's our volume. Times that by the concentration. So now we get the number of moles. So now we know the number of moles equals 0.0023. There's our number of moles. Now, if you look at this, 2 moles of sodium hydroxide give us 1 mole of H2SO4. So we always need twice as much sodium hydroxide. So if we need this much sodium hydroxide, we need half the amount of that we need half the amount of H2SO4. So that means the number of moles we have for H2SO4 are half of that. So that's going to be 0.0011. So now with H2SO4, we've got volume and we've got the number of moles. So if you think about the formula, moles equals concentration times the volume. So now we're rearranging that. We're trying to find out concentration. Concentration is going to equal the number of moles divided by the volume, which is 0.00116185 divided by 0.025. Well, in this case, they've done 25 divided by 1,000 to convert it to that, to convert to decimeters cubed, and that gives us a concentration of 0.0465. Now, if anyone would like me to go through that again, for those that are doing triple, I can, but it'll be at the end of the session. So, welcome everyone that's in combined. So we're now going to move on to electrolysis. So welcome, for those who have joined for combined, and I didn't speak to earlier, welcome to the final session of the AMALathon. Thank you to everyone that's been joining us live, and those who've been watching online afterwards, watching the recordings. Really appreciate everyone's attendance. It has been a really fun week. Tiring as well, because I'm not accustomed to talking for 8 hours straight, because I've been teaching AQA in the morning and Edexcel in the afternoon. So I've been doing 3 or 4 hours of each. So that was a shock to the system. Talking for 8 hours straight is not something I'm used to. But it's been fun. Really enjoyed it, and so thank you to everyone that's joined. And if anyone's feeling a little bit sad that it's finishing, don't worry, we're going to have AMALathon 2 starting soon. So you can register using the link below, join us on our WhatsApp channel, and keep up to date with everything that we're doing. If you've not had a chance to subscribe, please subscribe, and please keep sharing the videos. We really appreciate all the support we've had. We've had across the 5 days, we've had over 2,000 views of the AMALathon. So really appreciate it. Thank you. Okay, electrolysis. Now, once we've completed electrolysis, we are going to move on to topic 5, chemistry. The end part of topic 5 is triple award. When we finish topic 5 chemistry, that will be the end point for those that are doing combined, and then there's only triple topics to complete after that. So what is electrolysis? It's when an ionic compound is melted or dissolved. Now, another word for melted, you will have come across the term molten, or dissolved in water. Now, when an ionic compound is melted or dissolved in water, the ions are free to move. So if you think back to ionic bonding, and this is why ionic bonding and ions is such an important topic. Why can a solid ionic compound not conduct electricity? And that's because the ions have strong electromagnetic attraction between themselves, and so the ions are not free to move. They're so strongly bonded to each other, the electrostatic attraction is so strong that the ions are not free to move. But as soon as they become molten or melted, then the only thing, for example, if I've got an ionic compound, for example salt, in this beaker right now, it'd have to be a really high resistant to heat beaker. The only thing in here would be positive and negative ions, and the temperature is so high that the particles are moving so fast that they break free from the electrostatic attraction, and that means the ions can move around. Now, if the ions can move around when they're melted or in a molten state, it means they are free to conduct electricity. Now, the other scenario that they're free to conduct electricity is when they're in a liquid. So if you dissolve them, for example, salt in water. So when you dissolve salt in water, you get your positive sodium ions and your negative hydroxide ions. And again, they are free to move. But when you put electricity through that in electrolysis, you also, not only are you causing the dissociation of sodium chloride, the Na+. So not only do you have Na+ and Cl-, the water also dissociates. And the water dissociates into what we've just covered in acid and alkalis, H+ and OH-. So here we've got multiple ions. So when it's melted or in the molten state, it's a bit more, the electrolysis is a bit more simple because you only have 2 ions. The only thing that we've got here is Na+ and we've got OH-. But when you start talking about solution, when it's been dissolved in a liquid like water, then you've got multiple ions. You've got the Na+ and the Cl-, but now the water is also dissociated and broken apart. So now we've got an additional H+ and OH-. So when we're doing electrolysis within solutions, there's rules that we've got to remember. Now, if you understand what I've just explained on the previous slide, they are the key principles to understanding electrolysis. So electric current flows through the electrolyte. The electrolyte is a liquid containing dissolved or molten ionic compounds. So this is the electrolyte, this bit here that's been shown as purple. It wouldn't necessarily be purple in real life, it just is here to match the pink and purple colours here. But within that electrolyte we have got freely moving ions. And what does that mean? It means they can conduct electricity. We need the electrolyte to conduct electricity. And to do that, we need the ions to be free to move around. Then we've got negative. Let's look at the anode and the cathode first. So if you ever forget which one is positive, which one's negative, then panic. So P stands for positive. Positive is the anode. So this electrode here is the anode. And negative is the cathode. That should be a C. So this here is the cathode. And then within our electrolyte, and let's use the example of sodium chloride again, we've got Na plus, because sodium chloride splits apart into Na plus and Cl minus. Now we call positive ions cations, and we call, sorry, I've done that the wrong way around. We call positive ions cations, and a good way to remember that is cats have pores, so cations are positive. And we've got Cl minus, which is our negative ion, and they are called anions. Now a good way to remember that is anion is spelled a little by onion, and onions make us cry, and that's a negative. So I'm not saying crying is negative. Crying is good if you need to, but what I'm saying in this is just an association. So we've got the definitions here. Anode is the positive electrode. Cathode is the negative electrode. Electrolysis is the process of using electricity to break down a compound into simpler substances. So it's a decomposition. It takes a substance and it breaks it down. Electrolyte is a liquid or molten substance that contains ions and can conduct electricity. Now, one thing we should keep in mind here, the most popular or the most commonly used electrode is made of graphite. And if you think back to when we covered the topic on graphite, why would graphite make a good electrode? Number one, it conducts electricity. And if you think back, carbon can make 4 bonds, but in graphite it only has 3 bonds and it has 1 delocalized electron, which can conduct electricity. And second reason, it's unreactive, or it's fairly unreactive, particularly in the conditions for electrolysis. It does still degrade over time, but generally speaking it is unreactive. So let's look at the products of electrolysis. Now, bromide ions are negative. Let's look at this logically. Let's draw our 2 electrodes here and here. I'll read this out first. Bromide ions are negative and are attracted to the positive anode. Now, if they're negative, they are our anions. So our anion is negative and it's attracted to the positive anode. How can we remember which one is positive, which electrode is negative? We panic. Positive is the anode and negative is the cathode. Bromine is made at the anode, and lead ions are positive and are attracted to the negative cathode. So if lead ions are positive, they are our cations because they are positive, and they are attracted to our negative is the cathode, negative cathode. So let's break this down into a bit more detail. Let's look at lead bromide. So we have PbBr2, lead bromide. Now, once electrolysis has started, now first thing, this is molten lead bromide, meaning we have melted, or we have broken down. We melted the lead bromide. Now, once it's turned into a liquid, it's a liquid form, the ions separate. So what's the only ions inside this molten lead bromide? Just 2 ions. It's either Pb2+, or it's Br-. Now, is there any other ion in there? No. Now, the way you know there's nothing else there is this word. Can you all see which word? I'm assuming everyone knows which word we're talking about here. Molten. The word molten tells us there's only those ions, Pb2 plus and Br minus. So if we now say this is our positive anode, and we say this is our negative cathode, and the only ions in between in the electrolyte are Pb2 plus. So by the way, what I'm drawing at the top is like a zoomed in version of this. We've got Pb2 plus and we've got Br minus, nothing else. So we've got lots and lots of positive ions and lots of negative ions. So where is that Pb2 plus going to go? Let's start with the Br minus. Where's the Br minus going to go? It's going to go here. It's going to be attracted to the positive anode. And where's the Pb2 plus going to go? It's going to be attracted to the cathode. So I'm hoping this makes sense at the moment. That's what we've got to remember for this part. Now, if we go one step further, what's actually happening at these electrodes? So let's look at what's actually happening at each electrode. Let's bring this electrode back. And let's look at each one at a time. So let's first look at Br minus. Now, if you think of group 1, group 2, group 6, group 7 and ionic bonding, what's the only thing that can actually move? The only thing that can actually move is the ions, not the ions, what am I saying? The electrons. The protons don't move, the neutrons don't move. The only thing that transfers during the chemical reaction, or when bonds are made, which is a chemical reaction, are the electrons. So if you've got Br minus, what's that Br minus going to do when it gets to the positive anode? Br minus is Br minus because it's gained an extra electron. So it's going to give the anode its electron. So it's going to give away, it's going to lose its electrons. So we're going to end up with 2 Br minus, which will become bromine, as it mentions here, which is Br2. Remember, and don't forget, hydrogen, oxygen, nitrogen, and all of group 7 are diatomic. Plus 2 electrons, so it's lost those 2 electrons. So bromine has lost both electrons. So that means it has, if we go back to oil rig, oxidation is loss of electrons. So that means bromine has been oxidized. Now let's look at what happens to our Pb2 plus, our lead. Now lead sorry, I'm just trying to keep a little bit of space so I can actually write this down. So lead is Pb2 plus, and when it goes to the cathode is negative because it has more electrons. So it gains 2 electrons to balance out that 2 plus charge, and it becomes just lead. So that means at the anode we start to make bromine, and at the cathode we start to make lead, and we start to line that cathode with lead. So really quickly, if you've got malt ionic compound, you've got zinc chloride, zinc and chlorine. Molten ionic compound, zinc, and you've got zinc chloride. In electrolysis, what are the 2 products you're going to make? Well, the cathode is negative, the anode is positive. So the first thing you've got to look at is zinc chloride is going to be zinc 2 plus and you're going to have 2 chlorine minuses. So where's the Cl minus going to go? It's going to go to the anode, so that's why you get chlorine. Where's the 2 plus going to go? It's going to go to the cathode, so you get zinc. Lithium oxide, you get lithium plus and you get O2 minus. That means lithium plus will go to the negative cathode, and the O2 minus, which is negatively charged, is going to go to the anode, so you get oxygen. And when you come back to revise, I'll leave the rest for you to go through in your own time. Okay, so using electrolysis to extract metals. So we can do it this first way that I've just shown, when it's molten. However, it becomes a little bit different when, now everything that's here, I'll pause on each one, so when people are reading through, they can read through it and have a look at it. But this is what I've just explained on that previous slide. But I've explained it in a lot more detail, which is why I'm skipping through the slides and I'm just going past these questions as well. The one thing I will just go through is this second question here. Explain why a mixture of aluminium oxide and cryolite is used. So cryolite is a catalyst. So why do we use catalysts? Because they lower the melting point, they reduce the amount of energy needed. The catalysts reduce the rate of, they increase the speed of they increase the rate of reaction without becoming part of the reaction. Because they lower the melting point, they reduce the amount of energy needed. And this is a very good question as well. Explain why the electrolysis of aluminium oxide produces large amounts of carbon dioxide. And that's because the electrode is made of graphite. So the positive electrode, the anode, is made from carbon. So oxygen gas is released at the anode. So because in this particular case, oxygen gas was being released, because it was, in this example, it's aluminium oxide. So at the positive anode, oxygen is produced, and that oxygen reacts with carbon to make carbon dioxide. So that's a good question too. Now let's look at electrolysis of aqueous solutions. So the ions discharged when an aqueous solution is electrolyzed using inert electrodes depend on the relative reactivity of elements involved. So there are some rules when we're looking at this now. So when you're looking at aqueous solution, so again, let's use the example of sodium chloride. Now sodium chloride breaks up into Na+, which is our cation, and it becomes Cl-, which is our anion. But as it's in a solution, it means it's in water. And when you take when the electricity goes through it, and remember electrolysis when the electrical energy is used to cause it to break apart, to decompose. So the NaCl's become Na+ and Cl-. Now, on top of that, as electricity goes through the water also separates into H+ and OH-. Now, if you think about when we were looking at molten, what were the only two ions available? Pb2+ and Br-. There was no extra H+ or OH-. So when Pb2+ comes to the cathode, only the lead 2+ can react there. When the Br- comes across to the anode, only the Br- can react there. But when you've got a solution, more than one ion arrives. And if more than one ion arrives, you have to understand which ion is going to form, or which ion is going to be exchanging electrons, giving electrons or receiving electrons, losing or gaining electrons at the anode and the cathode. So the rules are as follows, and you need to memorize these. So at the cathode, the least reactive positive ion, so the least reactive cation, gets discharged. That's the one that forms. So hydrogen gas is produced unless there's a less reactive metal like copper or silver. Now if you look at, in our case here for the solution of sodium chloride, so the solution we're looking at is NaCl, a salt solution, we've got Na plus, H plus. We know Na plus is right at the top of the reactivity series, which means H plus is the least reactive positive ion. So what forms at the anode in this case? It will be, at the cathode, it'll be hydrogen gas that's produced here. H plus gas, so you'll see lots of bubbles around it. Now, hydrogen gas is produced unless there's a less reactive metal like copper or silver. So now if we had copper or silver here, the copper would form instead. Now, the rules for the anode are, if a halide ion, for example, anything from group 7, which is what we have here, if they're present, so anything from group 7 is present, it is discharged. So group 7 is made first. So the halide ion becomes a halogen gas, Cl2, Br2, I2. If there's no halide ions, then it's the OH minus that reacts. And the OH minus is discharged and oxygen is released, oxygen gas is released. Now you see this formula here, you need to memorize that formula. So if it's not a halogen, if it's not from group 7, then this is the half equation that occurs. 4OH minus becomes, so this is what's happening here at the anode. Either a halogen is produced, so a halogen gas, process. Even from my standards, that's not very nicely written. Write that again. So it's at least, it can be understood, at least it can be read. So halogen. So the halogen is produced. If there's no halogen, then oxygen is produced because the OH minus. This is the half equation for the anode at that point. So 4OH minus becomes O2 plus 2H2O plus 4 electrons. Now let's look at the different half equations that will occur. So we're using the example of sodium chloride. Now if it's OH minus, then we know this is the half-life. This one here. So if there's no group 7, then we know for the anode, that's the half equation. Now, if there's no group 7, if there is group 7, then what's going to happen? We'll have 2 Cl minus, and just as we showed before, when it reaches the anode, it loses its electrons to the anode. So you end up with Cl2 gas, and it has lost 2 electrons. So that is our oxidation. Both of these are our examples of oxidation. Now let's look at our example of reduction. The Na plus goes to the cathode and it gains an electron to become sodium. Now in both the redox and oxidation equations, the electrons need to be balanced, as there needs to be the same amount of electrons being gained and the same amount of electrons being lost. So if we were doing this properly, which we are, we'd double everything here. So here's just some examples for everyone to look through before. Again, have a look in your own time. We'll go through a couple. In fact, we'll go through the first 3, and then I'll leave the rest for you to go in your own time. Now, if this was molten, then this would be zinc, Zn plus, and we'd have Cl minus. So we'd have Zn2 plus, Cl minus, and at the cathode, which is negative, zinc would be formed. And at the anode, chlorine would be formed. But this is in solution. So that means we've also got H plus and we've also got OH minus. So we have to apply those rules that we just went through. So it's the least reactive positive ion that is formed at the cathode. So which one's the least reactive? In this case, it's H plus. So that means H plus, two of them both of them gain electrons to become H2, hydrogen. Here, now we're looking at the anode. And the rule for the anode is, if it's from group 7, that's group 7 is formed. If it's not from group 7, then the OH minus discharges there to release oxygen. And in that case, the half equation looks like this one here. Oxygen, 2 waters plus 4 electrons. So in this case, it's chlorine that's formed. And what's the half equation for it? Let's quickly draw it. We've got 2 Cl minuses become Cl2 and the 2 electrons that are being lost. So that's been oxidized. So all our oxidation occurs here and all our reduction happens at the cathode. Redox. Right, let's look at lithium oxide. I did say 3, but we'll just go through 2. So here we've got lithium oxide, so we've got lithium plus. We've also got, actually I will go through a third one. And we've got H plus as well from the water. We've got oxide, so that's O2 minus. And we've also got OH minus. So from Li plus and H plus, what's the rule for the cathode? It's the less reactive positive ion, which in this case is hydrogen. So the same thing happens. We end up with H2. Same thing as above. Now, in this case, we don't have a halide ion, which means it's the OH minus ion that is discharged. So you write out your balanced equation. So this is the half equation now. 4 OH minus becomes 2 oxygens. So remember, it's this formula here. Apologies, 1 oxygen and 2 H2O. So it's O2 plus 2 H2O plus 4 electrons. Now let's have a quick look at this one here. So we've got copper 2 plus and sulfur is SO4 2 minus, and we've got H plus and we've got OH minus, that's from the water. Now what's the least reactive H plus ion? It is copper 2 plus. So which is the least reactive positive ion? It is copper 2 plus, so it's going to be Cu2 plus, and because it's reduced at the cathode, it gains 2 electrons to become copper. And now we don't have any halide ions there. There's nothing from group 7. We've got OH minus, so it's OH minus that's discharged. So same as what we wrote here. 4 OH minus becomes, I'm going to repeat this so people are starting to memorize it. Oxygen plus 4 H2O plus 4 electrons. Done. Now we've covered both types of electrolysis. So I'm hoping now everyone feels a lot more confident with electrolysis. Now this is something I've already gone through. So I'm just going to pause there for a second. So when you're going through it, you can pause as well, you can read through it. But I've gone through the half equations at the positive and the negative, at the cathode and the anode. So the positive and the negative electrodes. Okay, and we've done this as well, where we've predicted. So let's go through some practice questions and then we're going to move on to topic 5. So water in the solution breaks apart to release hydrogen ions. So water in the solution breaks apart to release hydrogen ions. So the question is, why is hydrogen gas formed? So why is hydrogen gas formed at the negative electrode during electrolysis of potassium chloride solution? So before we even read the mark scheme, just understand it for yourself. So we've got electrolysis of potassium chloride. So that means we've got potassium chloride, which is potassium, which is group 1, so that's K+, chloride, which is Cl-. We also have, because it's a solution, we've got, so that means it's dissolved in water, it's aqueous. It's an aqueous solution. So we've got H+, and we've also got OH-. Now, the rule is, at the negative cathode, and what's the rule? The least reactive positive ion. Now that's from group 1, so that is high up on the reactivity series. So it's the H+ that's going to be discharged. So what does the H+ do? It goes to the negative cathode and it gains electrons to become H2, hydrogen. Let's see the answer now. Water in the solution breaks apart to release H+ ions. Potassium is more reactive than hydrogen, so it's hydrogen ions that are discharged instead. Now we said it the other way around. We said it's the least reactive positive ion that's discharged. That's absolutely fine. It makes no difference which way you say it. It's the hydrogen ions that are attracted to the cathode and they gain electrons from the cathode, and that makes hydrogen gas. Now you see those last 2 points there? That fulfills it. Now it says here, write the half equation for chlorine gas formation at the anode. So at the anode, let's look at these two. What's the rule for the anode? It is the halogen is made, and if there's no halogen being made, then what happens? If there's no halogen, then it'd be the OH-. Now in this case, we do have a halogen, so we're just doing the half equation for the halogen. So we've got Cl-. Now why am I doing 2 Cl-? Because chlorine always exists diatomically Cl2, so I need 2 chlorine minuses, and it's lost the electrons, so that's why I'm showing them on the product side. So I hope that makes lots more sense. Now this question, describe what happens to copper ions during the electrolysis of copper 2 sulfate solution. So once again, we can work everything out before even looking at anything else. We know we've got copper 2 sulfates, we've got copper 2+. How do we know it's copper 2+? Because those 2 lines there, the Roman numerals 2 means it's 2+. Also, we know that sulfate, or we should know that sulfate is 2-. Now, the water also dissociates, so we've got H+ and we've got OH-. So what's going to happen at the cathode? What are the rules? It's the least reactive positive ion. So what's the least reactive positive ion? It's copper this time. So what's going to happen? The copper is going to gain electrons from the cathode to become purified copper. Right, now let's look at the mark scheme. So copper ions are Cu2+, they're positive. They move towards the cathode, which is negative electrode. At the cathode, each copper ion gains 2 electrons. The ions are reduced and form solid copper metal. So we've covered all that. We didn't say it in those exact words, but this is why past paper practice is important. First we've got to understand, then we start to understand. We understand, then we memorize, and when we start applying it to past paper practice, the past paper practice, it refines how we're answering questions. It helps us to understand what the examiner wants. It also helps with memorization, because what's the best way to make flashcards? And I know a lot of you probably do make flashcards, but the best form of flashcards is question and answer, which means you don't actually need to make flashcards because past paper practice is already a flashcard. Past paper practice are already flashcards. And finally, the past paper practice shows you what you need to memorize. So that's our AMAL method, which I've said numerous times. Activate your brain, understand it, memorize. So that's activate your brain, memorize, and then apply to past paper practice. And that overall is the same. That equates to learning. Okay, excellent. Everyone, we're now going to move on to chemistry topic 5. Right, we'll take a 5-minute break and we'll come back to chemistry topic 5 at... We'll come back to chemistry topic 5 at 10:45. Okay, thank you everyone. See you all in Okay, welcome back everyone. So this is the final session for combined, and then we've got we're going to finish off the triple content linked to topic 5 chemistry, and we're going to cover the separate science triple content for physics P4 atomic structure, and then triple is finished as well. So if you have a quick look at what we've covered, we've done really well. We've managed to fit everything in into around 21 hours, which is excellent. All biology was finished yesterday. So biology is all done. Chemistry is done, and we've just finished C4. Excellent. And we're just about to start C5. Same with physics, P1, P2, P3, and we're just on the final part of P4 now. So not much more to go now. So let's get started. So energy transfers during reactions. So just excuse me 1 second. Okay, so let's continue. Chemistry topic 5. How does energy change in a chemical reaction? So it's not too big a topic, we've only got around 26 slides to go through. So if a reaction transfers energy to the surroundings, then the products must have less energy than the reactants by exactly the amount transferred. That's what we mean by conservation of energy. So all conservation of energy means is that the amount of energy that enters a system is the amount of energy that exits the system. So it's a law that states that the amount of energy in the universe at the end of a chemical reaction is the same as before the chemical reaction. So in other words, the amount of energy that enters is the amount of energy that leaves that system. Now, exothermic and endothermic. So when we say exothermic, we mean a reaction that transfers energy to the surroundings, usually by heating. Let me get rid of those lines. In other words, the energy is going out. So exit, exothermic. Exo, exit. Whereas endo means the energy is entering. Endothermic, entering. So a reaction that takes place so exothermic is a reaction that transfers energy to the surroundings, usually by heating. And endothermic is a reaction that takes in energy from the surroundings, usually causing a temperature drop. So our example of exothermic is, for example, respiration or combustion of methane. And an example of endothermic is photosynthesis. Also decomposition reactions. So just excuse me 1 second.
Oh, hi mate. Thank you.
Now, if we're doing an experiment to work out the energy transfer, we can use polystyrene cup and lid to reduce heat loss and energy transfer to the surroundings. So to explore how different variables impact on temperature changes, To explore how different variables impact temperature changes in reacting solutions, you can set up the equipment like the diagram shown. Now we use a polystyrene cup and lid to reduce heat loss or energy transfers to the surroundings. So polystyrene is a very good insulator, so it keeps the heat energy in. There's a lid at the top with a small hole so that we can add a thermometer so we can see the temperature change. So for this experiment, to detect temperature change, if the temperature increases, then what kind of reaction is it? It is exothermic. If the temperature decreases, then what kind of reaction is it? It is exothermic. Sorry, if the temperature increases, it's exothermic. If the temperature decreases, it is endothermic. So when we're doing this experiment, what we would do if we're doing this experiment, we would add an acid to the polystyrene cup or a reactant. Then we record the initial temperature of the solution. Then we add the test solution to the polystyrene cup. So we've got our initial. So what that means is you've got your polystyrene cup, you add your initial solution, you then add your reactant to it, you quickly put your lid on top, you put your thermometer inside. Now you've already measured the initial temperature, so you've got your initial temperature, you stir using the thermometer, and now what you do is record the temperature change. That means if it's exothermic, you increase the temperature it's increased up to. If it's endothermic, then you record the lowest temperature it gets to. Then you calculate the temperature change. So you've got the change temperature at the beginning, and you've got the temperature at the end. So you repeat steps 1 to 6 2 more times to check for outliers or anomalous results, and then you take an average. So let me just recap those steps. You've got your polystyrene cup. We're using that because it's an insulator. You add your liquid. It could be an acid or an alkali, whatever's being used for this particular reaction. You put a thermometer in there to check what the initial start temperature is, record that start temperature. You add your next reactant, so a reaction starts. Quickly put the lid on top. The lid has a hole inside, so you can put the thermometer inside. Give it a quick stir, and you leave it for a set amount of time. So the time that you leave it for is your control variable. So it could be 5 minutes, 10 minutes, whatever you decide, or whatever's decided in the method. After that, you now measured either the highest temperature it got up to or the lowest temperature it gets up to. Now if the temperature increases, then we know it is exo. If the temperature decreases, then we know it's endo. And then you repeat that process. So you've done it 3 times altogether. And then you remove any outliers or anomalous results and calculate an average. And you would do that with different test solutions. And with each solution, you are working out if it's an exothermic reaction occurring or an endothermic reaction that's occurring. So let's have a look at this exam style question. A student added ammonium chloride to water and then stirred the mixture. The water was in a glass beaker. His teacher said that using a glass beaker could cause inaccurate results. What could the student have used instead of a glass beaker to improve the accuracy? And give a reason why this would improve the accuracy of his results. So what we're saying, there's a lot in this question. There's a lot of, I suppose what you could call waffle. There's a lot of additional information that you don't need straight away. If you go straight to the question, all it's saying is what could the student have used instead of a glass beaker? So whenever we're doing these kind of experiments, what do we use? We use a polystyrene cup. So if we're trying to find out the increase in temperature of something, we're not going to use glass because glass, a lot of the heat energy will be dissipated or lost through it. And the second thing, give a reason why that would improve accuracy of results. So we use a polystyrene cup. That question is answered. And why would it improve accuracy? Because it's an insulator. So a lot of this extra info here is just to put people off. So whenever you get a question that seems a little bit off-putting, still read through it, or initially go to the question. So when you're reading through all the extra information, it has a context. Another really good question here. The student made sure his investigation was a fair test. State 2 control variables the student should keep the same. So 2 control variables the student should keep the same. And give a reason why changing each of these 2 control variables would affect the temperature change. So the first control variable is the volume of the solution. And why do we need to keep the volume of the solution the same? Because the greater the volume, the smaller the temperature change. So we can't have different amounts each time we do it. So let me repeat the question. We're saying 2 control variables and why the student should keep it the same. So the second control variable is the amount of stirring. Because when you stir, you cause the solid to dissolve into the liquid. So if you stir one more than the other, it means you've increased the rate of reaction in one compared to the other. Okay, so here's another question. This is a really good question. The question is just at the bottom here. So I'm just going to highlight it. This is a fantastic question to understand how to answer. This is the kind of question that shows the importance of past paper practice. Because this isn't something you're going to be able to memorize, you need to memorize, you need to have understood how to open up questions like this, how to analyze, how to understand a question like this, or how to answer it. So it says here, explain the conclusions that can be made from the trends shown in the results. So what we're looking at here is looking at the data and saying what can we conclude from it. So we can see here, as they've done this experiment, they use 0.1 grams, the temperature increased by 3. When they used 0.2, it increased by 6, 0.3 increased by 9, 0.4, 12, and it goes on until we reach 0.7. After that, it just stays at 21. Now there's a few things we can notice here. When it's 0.1, actually just to add a little bit of context, so you should look at this as it's an experiment where we've got polystyrene cup, we had an acid, and we've now added a magnesium metal into it. We've put up a lid over the top to insulate the heat energy and put a thermometer in there. Then we've come back to the experiment 5 minutes later and recorded the temperature change. So when it was 0.1 grams of magnesium, there was a temperature change of 3. Then it was 6 when it was 0.2. At 0.3 it was 9. Meaning every time we've increased by 0.1 grams, what's happened to the temperature? It's increased by 3 degrees. So our first conclusion is, every time we increase by 0.1 grams of magnesium, it causes an increase of 3 degrees in the temperature. That's conclusion number 1. The next thing is, after 0.7, it just stays at 21. Now we'll have a look at 24 in a second, meaning the reaction stops at 0.7 grams. That means everything we're putting in beyond that point, 0.8, 0.9 and 1 gram, is excess. Meaning at that point, 0.7 onwards, we've got to a point where all the acid has now reacted. The next thing we can look at is that number 24. It doesn't make sense that that's 21, that's 21, and that's 21. Suddenly we've got a 24 right in the middle. So what is that result? It's anomalous. Okay, now let's look at the mark scheme. Now if you look at that question now, you don't need to memorize something from beforehand. What you needed was understanding. You had to have understood, number 1, how to approach the question, and number 2, that once the number stops increasing, it means the reaction's ended. That means everything you're putting in after that point is excess. So look, let's compare what we've just said to the actual mark scheme. As the mass increases, the temperature increases, but after 0.7 grams, the temperature doesn't increase anymore. And we said exactly that, so that would be a mark. When the mass is increased by 0.1 grams, the temperature increases by 3 degrees. So another mark. The temperature rise is directly proportional to mass, so I missed that part out. But now we know, because we looked at our mark scheme, that that's something that needs to be added. And this is why past paper practice and mark schemes are really important. That should be your flashcards. Past paper questions should be your flashcards. Because these are the nuggets of information that we get from it. Then at 0.7 grams, no magnesium reacts. At 0.7 grams, magnesium is being added in excess. Okay, reaction profiles. So the first thing we need to understand, and when we cover rates of reaction in a lot more detail, which will be in our AMALathon 2, then the first thing you need to understand for a reaction to occur is 2 things have to happen. The particles have to collide with each other, and they also, not only do they have to collide, they have to collide with enough energy. And what do we call enough energy? The scientific the chemistry term for it is activation energy. That's the least amount of energy needed for particles to react. So that's why we've got a piece, for example, I've got a piece of paper on the table right next to me. There's oxygen in the air, but why is the carbon in the paper not reacting with the oxygen in the air? Because there's not enough energy. There's not enough activation energy. They're colliding with each other, but there's not enough activation energy. Now, if two particles have lots of energy, but they don't collide, there also won't be a reaction. So both things have to happen for a reaction to occur. Now, a reaction profile, they are diagrams that show the energy levels of reactants and products, the activation energy, and it also shows the total energy change during a reaction. Again, this is understanding. There's a few things I'm about to go through now, which is understanding, followed by lots and lots of practice. And if you understand it now, I would advise today, because our session was supposed to finish at 1 o'clock, and hopefully we're going to finish quite a little bit early before then. I would advise the time after that, I would go straight to topic 5. I would open up all the past paper questions, take one past paper at a time, and go through any question linked to reaction profiles and also calculating energy changes, which is what we're about to come to us after reaction profiles. So in an endothermic reaction, the products have more energy than the reactants. Energy has been absorbed into the surroundings. So let's have a look at what's happening here. We've got our reactants have got less energy. Now, let's say this is calcium carbonate. Calcium carbonate decomposes. So to decompose, it has to take energy in. Now, as it's taking energy in, what's happening to the amount of energy that's inside the calcium carbonate? So our reactant had less energy, but what's happening to the amount of energy? It's increasing. Because it's endothermic, all the energy is going in. And then that energy causes all the individual bonds. So calcium carbonate is CaCO3. The energy that's been taken in causes some of the bonds to break. So it breaks up into some of its individual components. Not exactly like this, I'm just giving this as an example. Now, when bonds reform, so in this case, they reform as calcium oxide and CO2, they release energy. And that's why the energy level decreases, just a small amount there. And so at the end, our products have a higher amount of energy. So there's a few things you need to understand from this. Number one, in an exothermic reaction, the reactants have less energy. It needs to increase by this much energy for the reaction to start. That's what we call the activation energy. It's represented by that line. And once the reaction started, because new bonds are being formed, some energy is released. But in the end, the products still have more energy than the reactants. The fact that the products have more energy than the reactants means it's endothermic. So the products have more energy than the reactants. Energy has been absorbed from the surroundings. Some has been released as well. Now, the big thing you should understand now is that in every single reaction, there's an element of endothermic and there's an element of exothermic. Now, if we say a reaction is endothermic, that means more energy was released in the endothermic part of the experiment. And if it's exothermic, it means more energy was released in the exothermic part. Now, I'm going to explain that in a bit more detail before we continue. And I'm assuming some of you will have heard this term, which is bendomex. So B for breaking. So breaking bonds is endothermic and making bonds is exothermic. So now look, let's go through this whole process again with this information in mind. Breaking bonds is endothermic and making bonds is exothermic. So now let's look at this whole process one more time. The reactants have got less energy and they start taking energy in. Now when they're taking the energy in, what are they doing? What's the energy being used to do? The energy is being used to break bonds. Remember, breaking bonds is endothermic. So this is the endothermic bit. That's why the energy levels are increasing, because energy is coming in, it's breaking bonds. Now that the bonds are broken, and it won't exactly be that it becomes calcium, carbon, oxygen separately like that. But now that the bonds are broken, bonds are made in a new form. Making bonds is exothermic. And when we have exothermic reactions, so when the bonds are being made, energy is being released. That's why the energy level slightly decreases there. But in the end, our products still have more energy than the starting point. And if that's the case, then it's endothermic. So that's the understanding behind it. But what do you need to memorize? You need to memorize this. You need to be able to draw it. You need to be able to add the activation energy line that starts from the reactants all the way to the peak. And then you've also got to be able to do this for exothermic. So I'm going to explain exothermic in exactly the same way. But now we've all obviously explained things in a bit more detail. I won't have to go into as much detail this time. So I'm just going to write here again, bendomex. And what does that mean? Breaking bonds is endothermic. Bendo. And making bonds is exothermic. I think I wrote bendomexo last time. Yeah, you don't need to write bendomexo, it's just, you can if you want, it doesn't make a difference. Bendomex. So now, let's look through this. The reactants have got a higher amount of energy. Now, initially, the reactants are taking energy in. That's why the energy levels increase. So that represents the endothermic part of this reaction. Then, once the reactants have been broken apart, and they now start making new bonds. So let's look at this. Let's look at an example. We've got HCl and NaOH, because neutralization reactions are exothermic. So what happens here is the Cl and the N, so our bonds break. So we've now got hydrogen separated from chlorine, so that's H plus and Cl minus. The sodium, because the amount of energy that's been given to it, is separated from the OH minus. That requires, to break those bonds, that requires energy. So energy has been absorbed. And that's shown at this initial phase here. So that's now our activation energy. So we needed this much energy for the reaction to start. So activation energy is there. Now, those are now going to, now that the bonds have been broken, they're going to reform in a new form. So the H plus is going to react with the OH minus. To become H2O. So now bonds are being made. That's exothermic. And Na is going to react with the chlorine to become NaCl. So again, new bonds are being made. So what happens? Energy is released. But in this case, more energy is released than was taken in. And because more energy has been released than taken in, our products have got less energy, and this is the reaction profile for exothermic. So again, what's the main thing here? Because that's the understanding behind it, and you will get questions that will look into the understanding. But what's the big part that you need to memorize? You need to memorize this reaction profile. You need to be able to show the difference between endothermic and exothermic. If a question comes on up where it asks you to explain, then it's what we've just covered. Now, what does that red arrow mean, representing figure 1? I'm hoping everyone said this at the same time. They were shouting at the screen. Although I can't hear you, I'm going to assume everyone knew the answer. Everyone should have been shouting, not shouting or saying to the screen, active activation energy. So that arrow there represents the amount of energy needed for that reaction to start. Now if we look at that energy profile, or the reaction profile, sorry, what does it represent? Exothermic or endothermic? And that could be a question in an exam. Is this endothermic or exothermic? Now we start with more energy and we finish with less energy. So that means it's exothermic. Because to break, when you initially are breaking bonds, the energy levels increase. That's endothermic. Then once new bonds are being made, energy is released. So in this case, a lot more energy has been released. That is exothermic. So bendo-mex. So I'll repeat that just one more time. Initially, energy has been taken in to break the bonds. So that's endothermic. So from this point to this point, it's endothermic. And when the bonds are being made, it's released energy, that's exothermic. So from that point to that point. So the exothermic element of the reaction was a lot more. The making of the bonds released more energy than the amount of energy that was taken in to break the bonds. So bendo-mex. So what do Y and Z actually represent? So we know Y represents activation energy, but Z represents the overall energy change. Now how do we know this is exothermic? And this is actually a very common question. And we've just gone through this. That's what the Z arrow is showing. But when you get questions, they might not have the Z arrow. They usually have the activation energy arrow. Sometimes they'll have the arrow that's labeled Z there as well. So how does the reaction profile diagram show that the reaction is exothermic? We know that because the products have lower energy than the reactants, indicating energy has been released. Okay, energy change of reactions. What happens to energy when bonds are broken in reactants and formed in products? So this is what I've already explained to you when I've said bendo-mex. So energy is required to break the bonds in a reactant. So energy is required, meaning energy goes in. So that's bendo. Breaking bonds is endothermic. And making bonds is exothermic. So energy is released when bonds are made. So when energy is being released, that's exothermic. Now, how is the overall energy change calculated using bond energies? So the energy required to break bonds and the energy released when new bonds are formed can be calculated using bond energies. So this is the next part that I just mentioned before, that is important for everyone to, as soon as this session finishes, to go away and memorize. So total energy change is the energy needed to break bonds. So remember, break bonds is endothermic. And from that we take away the energy released when bonds are formed, which is exothermic. So let's have a look at a question. So this is what we've already covered. Let's look at a question. Now I'm sure everyone's been through questions like this already, and there's going to be some of you that are already quite confident with this kind of question, which is excellent. So the question is here, it says use the bond dissociation energy. So this is bond dissociation energy in kilojoules per mole. So this is the amount of energy needed to break the carbon-hydrogen bond, which is 413. When you have a carbon double bond, it takes 614 kilojoules per mole. and so on. So that's the information that we've got there. But it's the same energy when you remake the bonds as well, or that's the assumption that we make when we're doing these equations. So you use these energies in the table to calculate the enthalpy change for this reaction. So we're working out the amount, what the change in energy is. So is it endothermic or exothermic? So the first thing we've got to do is calculate the energy needed to break the bonds. So we're just looking at this side here, because it is in the reactants that we're going to break the bonds. So if you look at the reactants there, what are the different bonds we're going to break? We're going to break a carbon-carbon double bond, so we need one of these. How many CHs? 1, 2, 3 and 4, so we need 4 of them. So that's going to be 4 times 413, 1 times 614. Then we've got a BR single bond, we're going to break one of them. So we need 1 times 993. Do we have any carbon single bonds? No. Do we have any carbon bromine bonds? No. So we don't need any of these. Okay, so we've got 4 times 413. Sorry, 614, that's carbon-carbon double bond, plus 4 times 413, plus 193. Add that all up. For bonds broken, we've got 2,459. Remember, at the end, we're going to do bonds broken minus the energy needed for bonds made. So that was just here. Energy needed to break the bonds minus energy released when bonds are formed. So what we've just calculated here is that to break all of the bonds here, 4 CH bonds, 1 carbon-carbon double bond, 1 bromine-bromine single bond, it took 2,459 kilojoules of energy. Right, now let's look at let's calculate the energy released when bonds are being made. So it's the exothermic element of it. So let's look at CH bonds first. We've got 1, 2, 3 and 4. Carbon-carbon double bonds, no, we don't have any of those. Bromine-bromine bonds, nope, don't have any of those. Carbon-carbon bonds, yes, we've got 1. And carbon-bromine bonds, we've got 2. So now we calculate all of that. We've got our carbon-carbon single bond, that's 348. We've got 4 CH bonds. We've got 2 carbon-bromine bonds. So add that all together, we now have the energy that's required to the energy required to make the bond. So in our previous slide, we worked out the energy needed to break the bonds was 2,459 kilojoules, and now we've just worked out the energy needed to make those bonds is 2,552. Now all we've got to do is bonds broken minus the energy needed for bonds made, which is 2,459 minus 2,552, which is minus 93. Now if the number's minus, it's only minus when we've lost more of the energy, because we're talking about internal energy here. So if something loses energy, the number is represented as a minus because it's lost that energy to the surroundings. In other words, this reaction is exothermic. It's exothermic because it has lost 93 kilojoules per mole of energy to the surroundings. It's lost the energy. If it is taking energy in, then the number will be positive because it's increasing in energy. Excellent. Right, that is the end of the AMALathon for anyone that's doing AQA combined. So thank you, really appreciate that you've been on with us for the last 6 days. I hope you've learned loads from it. Anyone that's watching the recording as well, really appreciate anyone that supported us. So really great big thank you. Like I've said to you guys before, in about a week's time I will send a post out, and anyone that has any questions can just send it through that post. You can actually just send the questions through these videos, as the last 6 days of videos as well. So the recordings for the AMALathon already have been uploaded. In fact, they get uploaded straight away. So you can ask questions directly on there. We have had a few students already asking questions, and I have myself and the team have already started to answer. We're happy to answer those questions. So what's the next phase for everyone? So really quickly before you go, we already know the first thing we need to do is we've got to understand everything. So that's the first thing we've got to do. We've got to activate our brains, understand everything. Now all these videos have been based on specification points. So when you're going through the video, you can see which bit you understand, which bits you don't understand. And also in the video, I have given you hints and tips on what to memorize. And then the phase after activating your brain, memorizing, is to start applying it to past papers. And why is past paper practice really important? Because it helps you understand what the examiner wants. It helps you to understand what key language could answer the question. It helps you to understand what's memorized, and best of all, it saves you from making notes because it is already built-in flashcards. The best way to use flashcards is to write a question on one side and answer on the other side. You've already got that built in. If you do all of that, you have learnt. In other words, you have AMALed. So I hope you guys have really enjoyed the AMALathon. Hopefully see you all in AMALathon 2. Okay, now, for those that are in triple, let's continue. Yes, Dean, there is a last section of physics, that's triple award as well. That's separate science as well. So if anyone that's doing, so the last part of P4, atomic structure, I got up to the triple award part and then I stopped. So at this point onwards, we're going to finish off the separate science part of chemistry, and then we're going to finish off the separate science part of atomic structure. So now it's just triple award only. Thank you, Dean. Right, now, I'm wondering how well people understand this topic. It is actually much more straightforward, kind of more straightforward than it comes across. So let's have a look through it. So initially you need to understand what a simple cell is, and then after that we need to understand what a fuel cell is. Now that's only 5 or 6 slides. 6 slides, but I will give as much time as needed. Now, a simple chemical cell is made by connecting 2 different metals in an electrolyte. So what we've got here is our electrolyte. Now why do we use electrolytes in electrolysis? Because an electrolyte has 3 ions. Okay, it's got freely moving ions. And what can freely moving ions do? They can conduct electricity. Now, the main thing we're doing in a simple chemical cell like this is we're converting chemical energy into electrical energy. Now, in other words, we're going to produce electricity. So the way it works is you have 2 different metals. Now, usually, for example, let's say metal 1 is magnesium and metal 2 is copper. Okay, then we've got an electrolyte, which is our solution that can carry ions. Brilliant. Now this combination allows a chemical reaction to take place, which sets up a flow of electrons. And if you think back to physics, what is electrical current? It's the flow of electrons. And what can metals do? What can the electrons from a metal do? They can dissociate and become free. And that means the electrons can travel in this wire. Now let's go through it step by step. So we've got our 2 metals, we've got our electrolyte. Now the more reactive metal, now what do all metals do anyway? So if you've got sodium, it's got 1 electron in its outer shell. What's sodium more like? What's sodium want to do that? What does sodium want to do with that electron? It wants to lose that electron. So here, what's the more reactive metal going to do? It's going to lose the electrons. So the magnesium is going to lose electrons. So that's going to become positively charged. Now, where is it losing the electrons? is losing into this wire here. So the electrons are flowing through this wire into this copper. So the copper becomes negatively charged. So if you look at this from a half equation perspective, what's happening with the magnesium is the magnesium is becoming magnesium 2 plus 2 electrons. Now meanwhile, what's happening in the electrolyte is the ions move through the electrolyte. That means the positive ions go to the metal, move to the copper. So you get positive ions going this way, and you get negative ions going this way. And so in other words, the ions move through the electrolyte to balance the charges in the cell. Now, in other words, they complete the circuit. And what you now have is a battery. So the flow of electrons through this wire is what we call electric current. Now, why does the voltage depend on the metals used? Each metal has a different tendency to lose electrons. So the more reactive a metal is, the more likely it is to lose electrons. So the higher up on the reactivity series, the more likely it is. Now, why do we use things like, why do we always use the second metal? Why is the second metal usually copper? Because the bigger the difference in reactivity between the two metals, actually they usually use zinc and copper. Zinc is more popular actually. Now, the bigger the difference in reactivity between the two, the bigger the push on the electrons. Now, what's another way of saying a push on the electrons? Voltage. So the bigger the rate of the amount of reactivity between magnesium and copper, the bigger the push, so the greater the voltage. Now, just gonna have a quick look to see if anyone's asked any questions. Yes, so in this case, the anode is the magnesium. The cathode is the copper. So the more reactive metal automatically becomes the anode. The less reactive becomes the cathode. I hope this makes sense. I'll explain it again. So what factors, I'm just going to read through this slide now and I'll explain the whole process again. What factors affect the voltage produced by a cell? So cells contain chemicals that react to generate electricity. The type of electrode and the electrolyte used affect how the cell works. Now at GCSE level, this is usually how it's explained, which is why I've gone into a bit more detail so it can properly be understood. Because the whole process, the whole point of this is that electrons flow from here and reach the second metal, and that ions flow, positive and negative ions flow to the respective. So if this becomes positive, we have negative ions flowing this direction, and we have positive ions flowing this towards the cathode, and we have a complete circuit. That's what makes up a cell or a battery. If you've understood the principle behind it, a fuel cell has the same principle. It's the flow of electrons, the flow of ions to complete a circuit. So the bigger the difference in reactivity between the two metal electrodes, the higher the voltage produced. Why do we have a higher voltage produced? Because when you've got something that's more reactive and something that's less reactive, it means there's a bigger push on the electrons that are being released. In other words, you have a higher voltage. So what are batteries? Batteries store chemical energy and then convert it into electrical energy. So look back here, that metal is a store of chemical energy. That piece of metal there is a store of chemical energy, they're metallic bonds. Once they release the electrons and the electrolyte is releasing the ions, what does it convert into? It converts into electrical energy through chemical reactions between electrodes, generating an electrical current. So a battery is made up of two or more cells connected in series to give a higher voltage. So the more individual cells, so the more of these that you have, so you can put lots and lots of these together, the more of these you have, the higher the overall voltage will be, as long as you've connected them. So the original cells that would have been made a few hundred years ago would have been really, really big. and they would have been full of these beakers to power something. Obviously now our batteries and cells are much smaller and much more advanced. Now, a point of note here is that alkaline batteries are non-rechargeable. But you don't need to know why in an exam. And rechargeable batteries and batteries can be recharged as their chemical reactions are reversible. That's essentially the main thing. Alkaline batteries, the reactions that occur inside them are not reversible reactions. So alkaline batteries do not have reversible reactions, but in rechargeable cells and batteries, they can be recharged as their chemical reactions reverse, as long as an external electrical current is supplied to it. So when you put it into the socket, you plug it in. Our main supply then provides the energy for the reverse reaction to occur. Okay, fuel cells. Now, if you think about how a cell works, the principles of a cell, the principles are exactly the same. So I'm just going to answer a question really quickly. Akshat, the combined part of AQA is finished now. Everything we're covering now will be triple award only till we finish. So we are finishing off topic 5 separate science, and we're going to finish off P4 atomic structure separate science as well. So everything from 5.2.1 onwards, 5.2.1 has been triple award. So fuel cells and that cell top, the cells and battery topic that I've just covered now is all separate science. So now fuel science, so a fuel cell follows the same principles. So let's show you what I mean. You've got a wire here. So when the hydrogen goes in, we want the hydrogen to release electrons, and we want the oxygen to take in the electrons. But the principle is the same. We've got an electrolyte over here. I'm just going to do it in a slightly different color. So this area here that I've highlighted has got an electrolyte. This area at the top that I'm just going to do with a red pen now has electrons flowing from the hydrogen to the oxygen. Now, the only thing with the fuel cell, the different thing is we don't need to use metals. What we're using instead is we're using water, essentially. Or we can use air, because we need hydrogen and oxygen. So we need a fuel. To fuel cells, they can be externally supplied. So fuel cells use an external supply of fuel, like hydrogen and oxygen or air. The fuel reacts inside the cell, producing electricity or voltage through a chemical reaction. In a hydrogen fuel cell, hydrogen reacts with oxygen to make water. The reaction releases energy. Now, this slide explains it in a lot more detail. I'm going to briefly describe it here again. I'm going to rub this out and explain it just one more time. I hope this makes sense. The hydrogen enters through here. Now, I'm going to explain it in basic terms on this slide, and we're going to go into a lot more detail on the next slide. Now, hydrogen is in group 1. So what's hydrogen going to do? It's going to lose that electron. So what's left behind is protons, essentially. Those electrons will transfer through this wire. And what does oxygen, which is in group 6, want? It's already got 1, 2, 3, 4, 5, 6 electrons. What does it want? It wants 2 more electrons. So it's going to gain the electrons this side. So in a sense, our anode here is going to be based on hydrogen, is going to be negative. Our electrode over here, our cathode is going to, no, sorry, let me just rub that out. Our hydrogen based anode is going to be positive because it's lost electrons. So like we just said, I'll just repeat everything because I made a mistake there. Hydrogen's got 1 electron in the outer shell, it loses that electron. So the electrons are going to flow through this wire. And because it's now lost electrons, we've got a positive anode with hydrogen gas flowing through it. And on the oxygen side, oxygen's got 6 electrons on the outer shell, so it gains 2 electrons. So this is our negative cathode with oxygen that's just been reduced flowing through it. And here we have an electrolyte, and that electrolyte's got 3 ions to complete the circuit. Now, so if we say this step by step, or better than step by step, let's actually see what occurs at each electrode. So at the negative electrode, two hydrogens react with OH minus. So this is the wrong way around. Yeah, sorry, this should say positive. So let me just start again. This should say positive electrode, that should say negative. So at the positive electrode, the hydrogen reacts with 4 OH minus, and it releases 4 water molecules, and it releases the electrons. So now the electrons have been released. No, sorry, I've explained one thing incorrectly. I'm just going to go back for a second. Apologies. It's not a major issue, but in fuel cells, the anode is actually the negative electrode. So this is the one difference between a normal cell. The anode is negative, and the cathode is positive. So it's the other way around. Now what happens at the anode, it just shows it here, the negative electrode, is that hydrogen reacts with 4 OH minus, releasing water and 4 electrons. So now the electrons are released. Now at the positive electrode, which is now in this case the cathode, the oxygen reacts with water, and it takes in those 4 electrons to become 4 OH minus. Now if you take everything from the reactants and from the products, and you add both of those half equations together, you get 2H2 plus 4 OH minus plus O2 plus 2H2O plus 4 electrons becomes 4H2O plus 4 electrons plus 4 OH minus. Now if we cancel out everything that's the same on both sides, the 4 OH minus cancels out, the 2H2O cancels out from here, you're left with 2 over here, and the 4 electrons cancels out. So what you're left with is 2H2 plus oxygen makes 2H2O. But within that process, what's actually happened? Electrons have flowed from the anode to the cathode, and then in this section here we have an electrolyte that is releasing ions. Now, one last thing we need to go through is the advantages and disadvantages. So the advantages of fuel cells are the only product is water. So there's no carbon dioxide, there's no toxic gases. It's more efficient than combustion engines, so it releases more energy than an engine that uses petrol or diesel. It works continuously as long as fuel and oxygen are supplied. So if you've got your supply of hydrogen, if you've got your supply of oxygen, it'll keep working. It can be used in vehicles, space missions, and it can be used as a backup power supply. Now, the negatives. Hydrogen is hard to store. It's explosive, and it needs high pressure. Hydrogen is often made from fossil fuels, so that means it might seem clean, but because it's coming from fossil fuels, it's not always actually clean. A bit like an electric car, if the electricity comes from fossil fuels, then it kind of defeats the purpose. Then fuel cells, they're expensive and they require platinum catalyst. So platinum within itself is really expensive. That's probably one of the most expensive parts of the engine that would be needed for it. And there's not really an infrastructure for it. So if there was a car that used fuel cells, there's not really an infrastructure. The same way we have an infrastructure for petrol. Okay, now we're going to move on to our final section. So we're going to take a 4-minute break while I get the PowerPoint loaded. So we're going to restart at 11:45. So I'll see you all in 4 minutes. So this is going to be our last section, the last part of our AMALathon 1. So I'll see you all in 4 minutes. Excellent. Welcome back everyone for the final AMALathon 1 2025 session, and we're now going to go through the final part of physics topic 4. And like I've said to you guys before, if you have any questions, welcome back everyone for the final. Like I said, if you have any questions, you're more than welcome to contact me or contact the team. And if you have any questions, you're more than welcome to contact the team through any of our videos, and we'll do our best to answer the questions as you're going through. So after this, the main thing we need to start doing now is lots and lots of past paper practice. Thank you, Samina, for your feedback. So, what are the sources of background radiation? So, background radiation, and we're going to cover this particular first one when we cover topic of space. So in AMALathon 2, in the last topic that we will cover in AMALathon 2 will be cosmic rays from space, and it's going to be linked to redshift and blueshift, or the Doppler effect, depending on how your schools taught it to you. So we'll understand in a lot more detail when we do topic 2. But it is one of the sources of radiation. So that's radiation that comes from the origin, potentially from the Big Bang. Then from rocks, because as you know, metals are found in rocks, so radioactive metals are within rocks, so that's the source of background radiation. So background radiation is radiation that's just always around us. Now if you used a Geiger-Müller counter to count the reactivity, it's wherever we are, it's usually around 10 becquerel. So there's usually 10 units of radiation around us per second, which is that's something that's always there due to natural sources. Then you've got some man-made sources that have released radiation. So that's fallout from nuclear weapons, or when countries have tested nuclear weapons, and also testing and nuclear accidents. So this is people that have thrown nuclear bombs, which is only one country during World War II, and this is the testing of nuclear bombs and nuclear accidents. So that, for example, Chernobyl, this also releases radiation into the atmosphere. So what effect can radiation dose have on a person? What can affect the radiation dose a person is exposed to? So one is occupation. So if someone is constantly, for example, someone who works as a radiotherapist, someone who does x-rays, a radiographer, does x-rays, they're constantly at risk of being exposed to x-rays, which is why they always stand behind that protective screen. And also location. So if someone is located in an area where there's more radioactive metal, or there could have been a radioactive accident, I think this is a picture of Chernobyl, then that could mean the same thing as well. So there was one village I remember reading about, and I think it was a village in Turkey, and what actually happened was they found that a lot of people in that village were getting cancer, as it was more than your average rate of cancer. And what they actually found in the end was that there was a little hill that was full of radioactive metal. So it was full of rocks that had radioactive metal, more than your usual amount. And that's why a lot of people are getting cancer within that area. So location does have an effect. Now, how can we measure radiation? So we measure it in sieverts, which is SV. Right, half-life of isotopes. So how does a substance's half-life affect its activity and risk? So radioactive isotopes exhibit a broad spectrum half-life values. So you've got some that last for a few days. So you've got substances, if a substance has a short half-life, its activity diminishes rapidly. That means that will lead to a quick reduction in the risk of harm as well. So you've got, for example, uranium can last in theory for millions of years before its activity halves. So the half-life for uranium is a few million. I think it's 4,500 million years, or 4.5 million years. I can't remember the exact number. Then you've got, for example, carbon-14, which has a half-life of around 7,000 years. And then you've got other ones like americium, or certain types of americium that can last for a little bit, can last for a few days or a few hours. So if you're using an isotope, you're using an isotope to detect where a blood clot is or anything like that, using it for treatment it's best to use something with a short half-life. That means the person will have some risk involved because they're in contact with the radioactive substance, but because it's got a short half-life, the activity diminishes rapidly, so it decreases really quickly. So within a couple of days or a few hours, won't have any harm. It won't cause any harm beyond that point, which is not too much of an issue. So what uses do we have for nuclear radiation? So the management of elimination of unwanted tissue. So we can use it for cancer treatment. So the image demonstrates this is radiotherapy, where radiation is utilized to destroy cells. So what that means is, so for example, if you've got like a really sensitive part of the brain, so that was supposed to be the brain. Let's assume that's the skull. Let's get rid of that. Actually, let's start again. No, it's fine. The brain's in the middle. Now, if the tumor is right there, then what you can actually do is you can towards it put low energy gamma radiation, or just fire gamma radiation in that direction. But you fire it in that direction from lots of different directions, so you can see because they all overlap on that one point where the cancer cells are. That's where you get an intense amount of radiation. Everywhere else gets a light dose, which can cause a small amount of harm, but it's not enough to cause destruction to the rest of the brain. So radiation can be used in that manner. X-rays can be used in that manner, gamma rays can be used in that manner as well. So the radiation used must have a half-life that's long enough to destroy the cells, but not so long that it causes additional harm. So what uses do we have for nuclear radiation in medicine? So I've just explained this actually. Examples include CT scans and the use of radioactive substances as tracers. No, sorry, I didn't explain that. So what this means is, in the CT scan, what you're able to do is inject a radioactive substance into a person, and as it flows through the bloodstream and starts to enter cells. Now, remember, this radioactive substance has a short half-life, so it's not dangerous. It has dangers attached, but it's short half-life, so it will dissipate. And what the CT scan does is it detects that radiation. So you can see, potentially if there's a blockage somewhere, you can see the issues straight away, where the issues are. So you don't have to do exploratory surgery, you can just find the issue straight away. Okay, nuclear fission. So nuclear fission, for fission to take place, the unstable nucleus typically needs to absorb a neutron first. So before, we showed how you can get, for example, uranium, and uranium can become thorium because it releases an alpha particle. But what happens in fission, it can still release an alpha particle, a beta particle, it can release gamma radiation, but it also can release neutrons. So here you might have, for example, uranium. Let me just get my highlighter. So you might have uranium here, which means it's already radioactive and it's unstable. Now, as soon as a neutron enters, this neutron here enters as an additional neutron, it causes even more instability, and then it causes it to start releasing radiation. So it might, for example, it will release 2 or 3 neutrons at this point, and it will also fission, meaning that big molecule will break apart into two smaller molecules. So nuclear fission involves the division of a large and unstable atomic nucleus. So usually when something's unstable, it will spontaneously release some radiation, so alpha, beta or gamma. But in this case, what's happened is a neutron has entered it and it's made it even more unstable, and that additional neutron has caused fission to take place. So the unstable nucleus typically needs to absorb a neutron first. It's absorb the neutron, and as soon as it's absorbed that neutron, the nucleus undergoes what we call fission. So let me explain that one more time. We've got an unstable atom, for example uranium. A neutron has entered that uranium, made it even more unstable, and then it fissions. It means it breaks apart. So it breaks apart into two smaller nuclei, approximately of equal size, and it releases these 3 neutrons. Now what those 3 neutrons do is they enter another uranium atom, another 3, which also go through fission and also release 2 or 3 neutrons alongside the fission product. So now we're going to have 9 atoms of uranium reacting, then 27 atoms of uranium reacting. So it's exponential. So the reaction increases exponentially. So along with the fissions process, 2 or 3 neutrons are released, and also gamma radiation, which is not shown in this. The fission reaction produces energy. So not only does it release the neutron, it releases gamma radiation, which is energy. Now all the products of fission carry kinetic energy. The neutrons that are released, they trigger further chemical reactions. So like I've just shown you, when one neutron enters the initial uranium atom, that can cause it to release another 2 or 3 uranium subatomic particles. Then when those neutrons, so the uranium releases 3 neutrons, the subatomic particles, they will have an impact on 3 more uranium atoms, which will then have an impact on 3 more each. So another 9, which will impact on 27. So very quickly you have a lot of energy being released from this nuclear, from the uranium, from the fission. Which is why we can use it in a nuclear power station, because that energy can be used to heat up water, turn it to steam. The energy can be converted into kinetic energy that causes a turbine to spin, and then that generates electricity. So the chain reaction in a nuclear reactor is regulated to manage the amount of energy that's released, because if that amount of energy that's being released is not regulated, it will just exponentially keep increasing. So it has to be controlled, and for that there's something called control rods. So what happens is you have your fuel rod that's got your uranium inside it, and you have control rods. Now the control rod is either initially at the top or at the bottom, depending on the design. And then if too much energy is being released, so what's happening in the control rods is all the uranium is fissioning. So when one atom of uranium, or whatever fuel it is, fissions, it causes more uranium atoms to fission, which causes more uranium atoms to fission. So as more and more uranium atoms fission, what happens? It can get to a point where too much energy is being released. So what these control rods do, they either move up or down, and they absorb some of those neutrons. By absorbing some of the neutrons, some of them, they just calm the reaction down. So those rods are very, very important, because if they weren't there, they would cause the nuclear power station to release too much energy. Okay, so and this is how nuclear weapons in theory would work. So the detonation of a nuclear weapon results from uncontrolled chain reaction. Okay, nuclear fusion. Nuclear fusion occurs when 2 light nuclei combine to form a heavier nucleus. So during the process, some of the mass is converted into radiation energy. So what that means is, so fusion provides the energy for the stars. In the stars, now this is a very basic explanation of what happens. You've got hydrogen and another hydrogen, and they combine to become either a heavy hydrogen, or they can combine to become a helium. Usually it becomes a heavier hydrogen first, and then after that, more heavy hydrogen combines to become helium. But you don't need to know that in too much detail. You do need to know what fusion is. So fusion is the fusing of 2 nuclei. Now when you look at something like a star, or for example our sun, it is too hot for the electrons to be in the electron shells. So remember what we said before, if the electron gains energy, it gets excited, goes to a higher energy level. In the sun, there's so much energy that gets absorbed, that so much energy in the electron in the sun, that the electron absorbs the energy and it dissipates. Which means what's actually joining together here is the nucleus, is the protons and the neutrons, to make the nucleus of the helium. Then the helium and hydrogen would join together to make boron. Helium and helium would join together to make lithium. Helium to combine together to make boron, etc., etc. So it gets heavier and heavier. But iron and beyond are only made within supernovas. So that's in heavy when really large stars become red giants and eventually explode. So this is an example here. That's your deuterium, which is a type of heavy hydrogen, and tritium, which is a slightly heavier hydrogen. When they combine, now what you've got to remember, inside a star, you've got a lot of gravity and you've got a lot of energy. So there's high levels of pressure. So you've got these nuclei are being pulled towards each other, and it's overcoming the electrostatic repulsion. So because they're both positively charged, the protons, as they come closer and closer, they push each other, they repel. But the gravitational forces of the star pull them towards each other. And that's there, and to the point that it becomes something new. It becomes helium, and it also releases a neutron. That energy that's released, the energy is what keeps that's the energy that's released from the star. So within the star, you've got two forces. This is something we'll cover in topic 8 in more detail, but I'm just going to quickly explain it. You've got gravity pulling everything inwards, and you've got this nuclear fusion that provides an energy outwards. And it's the balance between those two forces that causes the actual size of the star that we see. Okay, excellent. Thank you, everyone. That's the end of AMALathon 1 2025 for AQA. I've gone through the AMAL process with you multiple times, so please keep AMALing. If you AMAL properly and you activate, memorize and apply your learning, then you will get yourself to grade 9s. That's the best way to learn. So anyway, like I've said before, if anyone has any questions, thank you for all the positive feedback that I've had. Thank you for being on live every day for the last 6 days. So if anyone has a question, you just got to send it as a message into any of the last 6 days from the AMALathon, and someone from our team will do their best to get back to you as quickly as they can. Right, everyone, have a wonderful 2 weeks off, or remainder of the holiday. I hope you do amazing in GCSEs, and see you all in AMALathon 2. Welcome to welcome to day 6, the final session of Edexcel AMALathon. Welcome to day 5. Welcome to day 6. Today we're going to finish as much as we possibly can. Let's quickly have a look at the timetable. I'm going to highlight what we're going through today, and then we're going to make a quick start. Lots to cover today. So we're going to start with topic 5, biology. So we're going to finish topic 5, biology, in our first session. Then we're going to finish off chemical analysis or electrolysis part of that, extracting metals and equilibria in our second session. And then we're going to work through, then we're going to start radioactivity in our last session. And then there's some triple award content linked to radioactivity that we're going to finish in the triple session at the end, so at 4:30. Unless we've got questions, we'll answer the questions first. It's our last session. Now, what's really important for everyone to do as soon as these sessions are over is to start going through lots and lots of past paper practice. Past paper practice makes a massive difference. So my advice is, when this finishes, lots and lots of past paper practice. Remember, you've got to activate your brain, so understand everything. That's what we're doing right now. Memorize, and I'm giving you advice on what to memorize. And then finally, you need to start applying all your learning, and that's what will help you with overall. That will help you with your learning. That's what's going to help you with grade 9 standard, or if you're doing foundation, grade 5 standard learning. Okay, now with topic 5, there's a question. So this is the main part that we need to know about from topic 5, the WHO definition of health. So health is not just the absence of disease or infirmity, it's the state of complete physical, mental and social well-being. So that means it's physical well-being, mental well-being and social well-being. And that was the definition from the World Health Organization. So here's a past paper GCSE question linked to this, which was, which organization defines health as a state of complete physical, mental and social well-being, and not merely the absence of disease or infirmity? And the answer is World Health Organization. You could have written as World Health Organization, or you could have written as WHO. Describe the difference between communicable and non-communicable diseases. So the main thing we need to know here is the actual definition of each one. So communicable disease is a disease that can spread from person to person, and that includes things like bacteria, virus, fungi and protists. And a non-communicable disease is a disease that cannot pass from person to person. For example, things like cancer, things like diabetes. So you could be if you're stood next to someone with the flu, you could potentially get the flu. But if you're stood with someone who's got a heart problem, it doesn't mean the heart problem will pass on to yourself. So the flu is caused by a virus, TB is caused by bacteria, athlete's foot is caused by fungus, malaria is caused by a protist, which is then spread by mosquitoes. We're going to be learning about each one of those in a lot more detail. Now, things like vaccination, good hygiene practices, antibiotics, antivirals, which we're going to be going through in a bit more detail as we go through this topic, help to manage these communicable diseases. And what's a non-communicable disease? Diseases are non-infectious, and instead they're caused by factors such as diet, stress and genetics. So they cannot be passed from a person to another person. So there we've already said some examples: heart disease, diabetes, cancer, asthma. Now, and things like smoking, eating unhealthy food, not exercising enough, drinking too much alcohol, all these things can lead to non-communicable diseases. Now, this question here, it says, state two ways that communicable diseases are different from non-communicable diseases. And what are the main differences here? Communicable diseases are transmitted from one person to another. Communicable diseases are not inherited. Communicable diseases are caused by pathogens or you can give specific examples of pathogens. So any two from there, or you can put the reverse and say non-communicable diseases are not transmitted from person to person, or you could say communicable diseases are not caused by pathogens, or you could say communicable diseases, non-communicable diseases are inherited. So if you write the reverse of all those answers, you will still get the 2 marks. Okay, 5.3. Explain why the presence of one disease can lead to the higher susceptibility to other diseases. Meaning, if you get one illness, why might it lead to another type of disease? So that could be communicable causing non-communicable, some non-communicable diseases causing more communicable diseases. So we're looking at the connection between different diseases. So first thing we've got to understand is how the immune system actually works. So that's our body's defense mechanism. So it defends against infections. So if a person is infected with one disease, some infections can lead to multiple diseases. For example, HIV. HIV is a sexually transmitted disease, which we're going to cover in more detail in 5.5/6, and also there's a separate topic on it in 5.8, so it's just coming. It's passed usually through the blood, the semen, or vaginal fluids, so it's sexually transmitted, but it can pass through the blood as well. HIV infects the T helper cell. So when we say T helper cell at GCSE level, a better word for that would be white blood cell. You can say T helper cell. I have seen it in mark schemes, but it is the white blood cell. And that takes over. The HIV infects the white blood cell and takes over, using them to make copies of itself. So the HIV enters the white blood cell, this particular T helper cell, which can multiply, and it starts using it to help it multiply. The immune system can't respond properly to infections because it's the white blood cells that fight back against viruses and bacteria. So HIV patient means, so HIV itself starts to slowly destroy the immune system. If the immune system starts working properly, then the person will start to get other illnesses, and they'll get it in a way where it causes them more pain, or they're more susceptible to getting that illness, or they're more likely to get it on a higher, as it is, it'll cause them more issues because they don't have a strong immune system. And that is things like tuberculosis. It could lead to pneumonia, cold, flu, anything. Just a quick answer to this question, is this AQA? No, this is the Edexcel session. The AQA session was from 9:45 till 1 o'clock. Today was the last AQA session, but all the recordings are on our YouTube channel. So you can watch all the AQA recordings. This is specifically Edexcel. This is the last Edexcel session. But like I said, all the recordings are on the YouTube channel. So how the immune system works. So if someone's got the flu, when the flu virus enters the body, the immune system, the immune system immediately springs into action to fight off the infection. The nose hairs and the mucus trap the virus before it can reach the lungs. When the flu virus infects cells in the respiratory system, the body releases chemicals that cause swelling and redness. Now that leads to a weakened respiratory system, which means the person can potentially now get a bacterial infection like pneumonia. So this is just another example of how diseases interact. And there's lots of other examples. So things like someone's got diabetes, it can increase the likelihood of getting foot ulcers and potentially gangrene, which means having to get limbs cut off. So here's a quick question. Explain how the HIV infection affects the immune system and makes the body more susceptible to diseases like tuberculosis. So what does HIV attack? It specifically attacks the immune system. Now if the immune system is not working well, so HIV attacks the immune system, it specifically destroys the white blood cells, which play a crucial role in the immune system, in the immune response. So now if they have a weakened immune system, there's fewer white blood cells to fight infections like TB. Because the immune system is weakened, the body is able to destroy the TB pathogen or prevent it from spreading. That is an excellent answer to this question. This makes people with HIV more likely to get TB because their body can't mount an effective defense. So main thing here, if we look at the mark scheme, and this is the kind of question you need to memorize the mark scheme for. HIV attacks white blood cells, which play a crucial role in defending the body, leading to a weakened immune system. As a result, the body becomes less capable of eliminating pathogens like bacteria causing TB or preventing these pathogens from spreading in the body. So once it takes hold, it keeps spreading and there's not enough white blood cells to destroy it. Now describe a pathogen as a disease causing organism, including virus, bacteria, fungi and protist. So this is just a recall specification point. Communicable diseases like illnesses are caused by pathogens, and they're caused by pathogens such as bacteria, virus, fungi and parasites. Specifically and protists. And they can spread from person to person. They can be direct contact and there's lots of different ways they can spread. Now, viruses, this is just a quick explanation of what viruses do. If this is our cell, the virus comes along and it injects its DNA, it's a single strand of DNA into our cytoplasm. That cytoplasm, once it's in the cytoplasm, it makes its way to our ribosome, and as it enters our ribosome then starts making the correct protein. Starts making the protein that this single strand of DNA has information for, and it just turns out to be that protein that our own ribosome makes is actually a virus. So in other words, it takes over our machinery, and our machinery starts making lots and lots of viruses. Now, in the end, there's so many viruses left in the cell that it lyses, it breaks apart, and then those viruses leave, and then they can enter lots of other cells or do the same thing to other cells. Bacteria, on the other hand, they release toxins that damage cells and tissue. Protists are single-celled organisms. An example of protist is malaria, and then that's spread through a vector called a mosquito. So Plasmodium causes malaria. It infects the red blood cells, leading to fever and severe illness. So we're going to go through this in more detail in 5.5 and 5.6. State the meaning of the term pathogen. So what do we mean when we say pathogen? A pathogen, and this is what should be memorized now, it is an organism that causes disease. So it's a disease-causing organism. Now just note here, it says ignore examples of pathogen unless there's a link to cause. So in other words, just write what's there. What can a virus be classified as? So out of them four options, is it a bacterium? No. Is it a fungus? No. Is it a pathogen? Yes. And it's not a protist. So the only answer there can be pathogen. Now give one reason why. The common cold is described as a communicable disease. So all we're looking for here is a definition of communicable disease. Is because a communicable disease is one that can be passed or transferred or spread from person to person. And it says you can accept terms like contagious or infectious. 5.5 and 5.6, we're going to describe some common infections, and then we're going to explain how the pathogens are spread and how this spread can be reduced or prevented. Now, as I'm going through this, I'm actually going to be doing the triple award content at the same time, but I will let you know when triple award comes up. And you can always tell because it has a capital B next to the specification point. So let's keep moving on. There's a lot of memorization here, but I would advise going through past paper questions linked to this first, just to get an understanding of which questions are more common. HIV is one of the more common ones, as is tuberculosis, but any of them can come up. Malaria actually is another common one as well. So malaria is caused by a protist. Malaria is transmitted by mosquitoes. And what do we call a mosquito in this respect? We call it a vector. Malaria affects the liver and blood cells. So it affects the liver and it affects the blood cells. What is cholera? So cholera. Here's the symptoms: abdominal cramps, vomiting and diarrhea. How is it spread? Through contaminated food and water, particularly water. So it happens in it was a big problem in England a couple of hundred years ago when the pipe for sewage was mixing with the pipe for water. So the source of water that was for drinking and the source of water for sewage were mixing, and that was spreading cholera. Now the best way to deal with it is controlling spread is oral rehydration solutions to prevent dehydration and also a vaccination. But because a person has a lot of diarrhea and they're vomiting, it means they're not keeping in enough water. So the whole point here is drinking lots of water. So oral rehydration tablets help with that. What is cholera? So that's not something we need to look at the moment. So what is tuberculosis? It's a persistent coughing, which can include coughing up blood, loss of appetite, tiredness and fever. Now, how is it spread? It's spread through droplets from coughs and sneezes through the air, so spread through the air. And how do we control the spread? It can be treated with antibiotics, and there's also a BCG vaccine. Coughing and of course coughing and sneezing into a tissue. So general hygiene and etiquette when a person is ill should be followed too. And that's with all of these illnesses. What is cholera ash dieback? So this is something that affects leaves or affects plants. So it's discoloration of the leaves, leaf loss, it causes bark lesions, and eventually the death of a tree. Now, the whole point here is that if you've got discoloration in the leaf, I probably would have been better if I'd done this in green, but assume this is green now, and you got these extra colours added in. They're not green. What that means is anything that's not green means there's no longer chlorophyll there or chloroplasts. So within the chloroplast, you have chlorophyll. Chlorophyll is part of the chloroplast that absorbs the sun's energy and then combines carbon dioxide and water and causes turns carbon dioxide and water using the sunlight's energy that's just absorbed and turns it into glucose and oxygen. And that glucose and oxygen, so in that process is photosynthesis. So the more of this that is coloured, because it turns to a colour that's not green, means less photosynthesis. That's why eventually there's less glucose for respiration, for growth, because it's glucose that gets turned to proteins. So that's why you end up with leaf loss, bark lesions, as in where the bark's not growing properly, and eventually the death of a tree. And it's spread through the air. How do you control the spread? Collect the fallen leaves and destroy them. In some cases, just to dig up the plant and to get rid of it. Cholera ash dieback, and how does it affect growth? So this is what I've just explained to you. If less of this leaf is green, then you've got less photosynthesis. So it says here, cholera ash dieback is a fungal disease that damages leaves, stems and branches. It reduces photosynthesis. Why? Because it's destroying the chlorophyll. So less of the sunlight's energy is being absorbed, and that slows down the tree growth. Severe cases can cause branch dieback and tree death. Now, you don't need to know about branch dieback. The main thing is that the branches, the leaves start to fall. The more that the tree loses, the less photosynthesis it does, and the closer it gets to death. What is malaria? So mosquitoes, and some of you will know this and some won't, depending on if anyone's had an encounter with a mosquito, they will know they've had an encounter with a mosquito. Because it is an annoying thing. They just buzz around and they don't stop till they've bitten you multiple times. So the mosquitoes feed on the blood from an infected person. So if a mosquito comes along and it feeds off the blood of someone who's infected, then when they feed off another person, they can pass that plasmodium, the protist, on to another human being. The mosquito doesn't get sick itself, but it does spread the disease. And an organism that spreads the disease we call a vector. So this is a vector. So malaria, the symptoms of malaria are fever, sweat, chills, headaches, vomiting, diarrhea. We know that mosquitoes are the ones that spread it. And how can it be controlled? Well, mosquito bites can be prevented by using nets and repellents. You can remove and drain stagnant water because that's where mosquitoes breed, and you can spray insecticides in areas with still water. There's also anti-malarial drugs that can be taken to treat symptoms and prevent infection. HIV. Now this is going to be covered in a lot more detail. So I'll come back to it in topic 5.8. Stomach ulcers. So this is caused by bacteria called Helicobacter pylori. Now you don't need to know the name of that, you just need to know that it's caused by bacteria. They live in and damage the stomach lining. It's really common, it's a really common infection. Some people suffer from symptoms and others don't. So it can cause indigestion, a loss of appetite, heartburn, and it's spread through oral transmission or direct contact. And controlling spread, you can use antibiotics, and there's medications that reduce the stomach acid as well. So things like Reni, Gaviscon, that kind of thing. Okay, Ebola. This is a highly deadly viral disease caused by the Ebola virus genus. So the main thing we need to know here is that it's caused by a virus. You don't need to know the name of Ebola virus. Now, unlike HIV, which primarily weakens the immune system over the years, Ebola causes severe acute symptoms and has a much higher fatality rate, ranging from 50 to 90% in severe outbreaks. So this causes fever, headaches, joint and muscle pain, muscle weakness. The patient develops diarrhea, vomiting, stomach pain, internal bleeding. So it causes a lot of symptoms really quickly. Whereas something like HIV virus slowly breaks away at the immune system, and it can take a few years, unless they take antiretrovirals, which helps to live a lot longer. Something like Ebola doesn't last for a few years; it happens in a few weeks. Now, it spreads through direct contact with bodily fluids of infected individuals or contaminated surfaces. Now, in terms of controlling spread, there are currently no treatments. Prevention involves avoiding body fluids of infected people. So there are antiretrovirals which slow it down. There's no treatment. I'm thinking of HIV. Okay, 5.7b is triple award. So if you're doing combined, it's only going to take about 2 minutes to go through, and then we'll continue. So in the life cycle of a virus, there are two pathways, and I'm just going to zoom in to explain that. So here's our two pathways. Person gets infected. Now, here's the virus. Let's get the pen back. Here's the virus. It's injected. Now let's use bacteria as an example. So this is bacteria. The virus has injected itself into the bacterial cell. Now what the virus has actually done is that's a little bit of viral DNA. I mean, it's showing as a double helix, but it's not a double helix, it's a single strand. It attaches itself to the plasmid. Now in human beings, it attaches itself to it just goes straight to our ribosomes. So it's there. Now what happens is, this bacterial cell multiplies, but what's it multiplying with? It's multiplying with the genetic information for a virus, to produce a virus. Now, due to whatever occurring, so there's something that may happen to the bacteria. Now, if it's in a human being, there could be a certain illness we get. There can be something that occurs in the body which triggers these cells. So imagine if it's in a human cell, it means every cell that's come from that one cell now has the DNA to create a virus. Now something triggers, and suddenly it starts to produce viruses. It starts to produce lots and lots of the virus, until there's so much of the virus inside there that the cell lyses, it breaks apart, and now those viruses are free to go and infect again. Now let's look at the lytic cycle. So now what can happen is, so I'll go through this cycle a few times. So we've got our single strand of DNA. This time it's not integrated. When we look at the lytic cycle, there's no integration. Instead, it goes straight to a ribosome, and the ribosome starts making lots of viruses, and until there's so much virus, it breaks free, and then it infects a cell. Let's look at the lysogenic cycle. Back to the viral DNA or single-stranded DNA, so mRNA, it integrates itself into the plasmid, or if it's a human being, into the DNA. At this point, the bacterial cell doesn't really know about this extra gene, so it starts multiplying. But what's it multiplying with? It's multiplying with the DNA to make a virus. Now, due to some sort of environmental factor, the gene kicks in, and lots of viruses are produced, and then the cell lyses, breaks apart, and the cell gets infected. Now we're looking at the lytic cycle again. This is where the viral mRNA, single strand of DNA, is injected into the host cell, and straight away the mRNA, the ribosomes start producing this new protein, which is the virus. Lots and lots of viruses get made until there's not enough room for them, so the cell breaks apart and the viruses go free, and they go and infect a host cell. So what this means is, when a virus infects a cell, two things can happen. Either the lysogenic cycle, which still ends up with lysis, or the lytic cycle, where it infects and starts destroying cells straight away. So in the lytic cycle, the virus injects its genetic material into the host cell. The newly made viral proteins and genetic materials are put together. The viral genetic material takes over the host cell's machinery, forcing it to produce copies of the virus. Now, in the lysogenic pathway, the virus attaches to a host cell and injects its genetic material into the cell. The virus hides inside the host cell's DNA, and it's copied every time the cell divides. A trigger such as stress or a change in the environment activates the viral DNA, which then enters the lytic cycle. Okay, now I'm just going to show you this question. It says viruses can cause disease through the lytic and lysogenic pathways. Explain how the lytic pathway leads to the reproduction of viruses. So the virus, this is a really good question to memorize. The virus injects its genetic material into the host cell. It uses the host cell structures such as organelles and resources to produce viral components like proteins and genetic material. In other words, it uses the ribosomes to make another version of itself. These components are then assembled to form new virus particles inside the host cell. Finally, there's so many of those virus particles that the cell bursts or lyses, releasing the new viruses to infect other cells. Okay, I hope that makes sense. We're now on 5.8. How are sexually transmitted diseases, STIs, are spread and how they can be reduced or prevent infection. So chlamydia is a common STI. It's caused by bacteria. It can affect both men and women and spreads through unprotected sex. So bacterial infection. What is chlamydia? So its symptoms are swollen testicles in men, bleeding between periods in women, and it's spread through sexual transmission. And the control is using a barrier method of contraception such as condoms, and it can also be treated with antibiotics. HIV is a virus that attacks the immune system, making it weaker and less able to fight infection. So it's a viral infection. So HIV, initially it causes flu-like symptoms, and again it is spread through sexual transmission and exchange of body fluids such as blood. And to control the spread, you can use things like condoms, barrier method contraception, and needles should not be shared. So this is one of the common ways that it's spread in the past as well, where people share needles, people on drugs, for example, and they've passed on HIV. Some people passed on HIV to others. So give one way. So only one more question. One way transmission of chlamydia can be prevented. So it could be avoid sexual contact. It could be using a condom or a femidom, as in a barrier method of contraception, or screening people for infection to identify and treat cases early and treat the infection using antibiotics. Now, chlamydia is caused by bacteria, so we can mention that. Okay. 5.9, 5.10, again, triple award. They're not particularly long topics. And there's a couple of questions. I'm going to go straight to the questions because the questions summarize everything. So how do plants chemical defense? How do plants chemically defend themselves from infection? So they can release antimicrobial chemicals. The leaf cuticle is a waxy waterproof layer that covers the surface of leaves and stems. It acts as a physical barrier to protect plants from water loss, pathogens and insect damage. So this is the actual question. How do plants chemically defend themselves from infection? Antimicrobial chemicals. So some chemicals are toxic to pests and pathogens. So plants release antimicrobial chemicals. For example, some plants release compounds that interfere with the growth or reproduction of fungi and bacteria. An example of that is sage. So, explain how plants defend themselves from being eaten by pests and from diseases caused by pathogens. So the answer to this is physical defenses and chemical defenses, because it's a 6-mark question. This is the question I was trying to get to. So physically, plants' leaves are often coated with a waxy layer, so cuticle, which acts as a barrier to pests and pathogens. They have a cell wall that's made of cellulose, and that provides structural support and are difficult for pests and pathogens to penetrate. Some plants have specialized structures like spines or hairs that deter herbivores. So this 6-mark answer, if you memorize it, it covers the whole of this topic. And from a chemical perspective, plants produce chemicals that are toxic to pests, reducing the likelihood of being eaten. Certain chemicals have antimicrobial properties that help prevent infections by pathogens. And plants may produce substances with unpleasant tastes or odours to repel pests as well. Okay, 5.11. This is how can we actually identify the plant diseases. So again, I'm going to go to the 6-mark question that was asked on this topic, because it brings everything together. So plant growth can be affected by environmental factors, pathogens or both. A farmer notices lesions on crop plants growing in their field. Discuss how this issue could be investigated. You refer to both field work and testing methods. So that's two different answers that have been mixed into that one. So one is rule out environmental causes. So you check for stunted growth. So I'm just going to go through the answer now using the PowerPoint slides. Stunted growth, look for powdery mildew, black mold or slimy patches. It affects the whole plant evenly, especially the lower leaves first, unevenly, and it can lead to, there's another thing you can look for is malformed stems or leaves or discoloration, yellow leaves. So when you're trying to work out what plant disease initial is, you rule out the environment. If you're looking at trying to find out what the plant disease is, initially you need to rule out environmental causes. Then you can analyze the distribution of affected plants in the field. So if a disease is spreading through a field, it often follows a pattern. For example, diseases caused by soil-borne pathogens might appear in appear in patches, while other diseases might be spread that are airborne. Observing how the disease is spread can provide clues about its cause. Next thing, analyze the distribution of affected plants in the field. So you look for yellowing. That means there's a deficiency in nutrients, or viral infection or root damage. Wilting, that could be a fungal or bacterial infection. It could be root rot or water stress, meaning there's not enough water getting to the leaves. And then we've got viral infections. They can be called mottled leaves, as in, again, it's a type of discoloration. How can plant diseases be detected? So step 4 is diagnostic testing. So you could culture the pathogen, and what that means is taking a petri dish that's got starch agar inside it, so it's got nutrients to help the pathogen grow. Then adding the pathogen from the plant to the agar and allowing it to grow. So identifying fungal spores, bacteria, and then after that you can look for fungal spores, bacterial colonies, or microscopic pests. It gives you a better understanding of what's actually causing the disease. Detecting specific pathogens at the genetic level, so you can do genetic analysis as well. Fungal spores can be cultured on agar plates. This is what this part is. And you can observe their growth patterns that gives you an understanding of what it would give the scientist or the person looking at the plant understanding of what the disease is being caused by. And using testing kits with monoclonal antibodies to identify the pathogen as well. Okay, 5.12. So we're back to combined. This is for everyone. So now we're looking at how physical barriers and chemical defenses of the human body provide protection from pathogens, including physical barriers like mucus, cilia, skin, and chemical defenses like lysozymes and hydrochloric acid. So I know this is a well understood topic, but if you have any questions, please ask. So how do we defend ourselves physically? Well, do we defend it with the skin? So that's like scabs. We also have nose hairs, mucus in the trachea and bronchi, cilia in the trachea and bronchi. So skin, we've got a dead layer of skin, or we have skin cells which is difficult to penetrate, so it acts as a barrier. And if we get cut, we form a scab that then becomes a defense while the body heals the skin. Nose hairs, the nose hairs and the cilia, because we've got cilia at the bottom there, they both keep dust and microorganisms out. Now I'm going to go, we spoke about nose hairs, I'm going to go straight to cilia first. They're tiny hair-like structures that line the respiratory tract, so your trachea and your bronchioles, and they sweep mucus out of the respiratory system. Now, as we're breathing in, all these tiny hairs, they trap the dust and the microbes. When the cilia start sweeping the mucus out of the respiratory system, the mucus in the nose and the throat capture pathogens, stopping them from reaching our lungs. So we start flicking up the mucus upwards, and the mucus that's been flicked upwards, it eventually comes to the top of our trachea. And when it's reached the top of our trachea, we either spit it out or more commonly we swallow it. And then our stomach acid deals with the rest. Now these are our chemical defenses. So our eyes contain lysozyme enzymes. And those lysozyme enzymes, if any germs come onto our eyeballs, our eyes, then the lysozyme is an enzyme which breaks down the bacteria. Our saliva helps kill bacteria in the mouth as well. Mucus is technically a chemical, so it helps destroy bacteria in the respiratory system. Our sweat also acts as an antimicrobial barrier on the skin. Then we've got stomach acid. So it is a strong acid, so that means if you eat food that's got bacteria inside it, the hydrochloric acid kills the bacteria before it can reach our small intestines or any other part of the body. Right, here's a really good 6-mark question that brings everything together. Describe how the human body's physical barriers and chemical defenses protect it from diseases. So mucus produced by cells lining the body surfaces trap pathogens. Cilia found on the cells of the respiratory system move mucus out of the body or into the throat. The skin acts as a thick waterproof barrier, and there's additional defenses like tears washing away the pathogens. We've got earwax trapping pathogens and nasal hairs filtering particles. Now from a chemical defense perspective, we've got lysozymes found in tears, saliva and the mucus, and are enzymes that kill certain bacteria. And the hydrochloric acid in our stomach has got a low pH, meaning it's very acidic, strongly acidic, and that destroys many pathogens too. Okay, 5.13. Now we're looking at the immune system and how it actually works. And what it does is, we have a pathogen that comes into the body. So, and what pathogens have, for example, bacteria, they have this protein group on the outside of it called an antigen. Now, initially, when a new bacteria or virus enters the body, it's the first time it's encountered this particular bacteria or virus, so the body doesn't know how to kill it off, so we get ill. Now, eventually, the body makes the correct white blood cell that has the correct antibody, and when all those antibodies are released, they attach to these antigens and they stop these bacterial cells from working. In other words, they neutralize the pathogen. So look, we've exposure to the pathogen. The pathogen carries a unique protein on its surface called an antigen. Lymphocytes are a special type of white blood cell that detect antigens and produce antibodies to neutralize the pathogens. Now, what will happen is, because these antibodies, lots of these bacterial cells will be clumped up together, and there's a type of white blood cell that will come then engulf all these bacteria and destroy them. Now, what will happen when the correct white blood cell has been made by the body quickly multiplies them, so we have lots of them. But once this bacteria is dead, there's no need for that many white blood cells. So what the body does, it destroys many of them, but it keeps a few behind as memory cells. And that is just in case that particular bacteria or fungus comes back to the body, we already have the lymphocytes ready to destroy it. And now if that same bacteria comes back, these memory cells rapidly multiply and destroy that bacteria. Now, that means from a secondary perspective, the second time round when a bacteria comes into our body, we don't get ill because we already have the memory cells. We already have the lymphocytes ready to attack and destroy that particular pathogen. Now, vaccines work in exactly the same way. So let's quickly do this. Describe how the immune system defends the body against disease. Pathogens have antigens on their surface. So this is another very good question just to memorize. They've got antigens on their surface which are recognized as foreign. These antigens stimulate the production of antibodies by lymphocytes. So the antigens stimulate the production of antibodies by the lymphocytes. Lymphocytes are white blood cells. So as soon as these white blood cells detect the antigen, it makes the correct antibody. The antibodies bind to the antigens, leading to the destruction of the pathogen. Now, how do vaccines work? Immunization or vaccines work in exactly the same way. So you know how we just said the bacteria comes in and it has antigens. This time, exactly the same process occurs. The body makes the correct white blood cells with antibodies, etc., etc. It destroys the bacterial cell, and in the end, a few white blood cells are left as memory. The only difference is this is a dead version of the cell. So the bacterial cell with the antigens that enters the body is a dead version of it. Meaning it's dead or a weakened version, so it won't cause the real illness. It might cause light symptoms, but it's not going to lead to death, or it's not going to lead to any major problems. So so immunization works by introducing an inactive or weakened form of the pathogen into the body. These antigens do not cause disease, but they're still recognized as foreign by the immune system. They still have the same antigens as the real thing. So that means it leads to a response from our white blood cells, and then our white blood cells destroy the vaccine, the dead or weakened version, and some are left behind as memory cells. So now when the real thing comes along, as in the living version, our body already has the defense system in place, and hence we don't get ill from the real thing. So things like when we were all little, most people would have had the MMR vaccine, mumps, measles and rubella, which means as we're now older, it's possible that we've breathed in that particular bacteria or virus, but we've now got ill because we already have the memory cells to destroy it. So vaccination makes children immune to Clostridium tetani. So this question is explain why these children do not develop tetanus if the bacteria enters the body through a cut in the skin. So vaccination makes children immune to Clostridium tetani. The vaccine contains antigens from bacteria which stimulate the immune system. This results in a faster secondary immune response, killing the bacteria before the disease develops. Okay, 5.15b is the advantages of immunization, and this is a triple topic. So this is only going to take a couple of minutes. What is herd immunity? Herd immunity occurs when a large percentage of the population becomes immune to a disease, making it difficult for a pathogen to spread. So that means so many people have been vaccinated that it makes it difficult for the virus to spread from person to person. Because in between one person and another person that's not been vaccinated, there's lots and lots of people that have been vaccinated, and those vaccinated people don't pass on the illness. And that then protects people who are newborn or who have, for example, they may have allergies towards the vaccination, and so they can't take vaccines, or just people who haven't been vaccinated. Now, it's an advantage in some respects because it protects against the disease. Herd immunity protects those who cannot be vaccinated, like those who are newborn or immunocompromised individuals, as in they have issues with the vaccine, they've got allergies, and it's cheaper to vaccinate than to treat. So if everyone's vaccinated, then no one's going to get ill, and they won't have, not as much money will have to spend on medicine. But it does have side effects. Some people may experience mild reactions like fever or soreness, and it's very, very rare, but it does happen where there's some serious side effects. Cost and accessibility. Some vaccines can be expensive or difficult to access in certain parts of the world. Also, it's not 100% effective. Some individuals may develop full immunity. Some might not get full immunity, so sometimes there is a need for booster injections. So let's have a quick look at this question. State two reasons why people might not be immunized against measles. So one, there could be some people who are concerned about potential side effects. So there are people who don't get vaccinations. So sometimes it's because they're concerned about side effects or allergic reactions. Sometimes medical conditions, that they have pre-existing medical conditions that prevent them from taking vaccinations because they already have a weak immune system. So even a weakened version could make them ill. It could be because they're babies and they're too young. Or it could be a lack of access to healthcare services. Okay, antibiotics. Antibiotics are medicines used to treat bacterial infections by either killing the bacteria or stopping them from growing and reproducing. So they only kill bacteria. So the key point here is they do not kill viruses. They only kill bacteria. So no one should be writing that they kill viruses. And how do they work? This is the key point. They kill bacteria, and the key point here is they kill bacteria by destroying the cell walls or disrupting essential processes. That is an answer to a 2-mark question. I think it's from 2 or 3 years ago. Okay, now this is just a bit of history, you don't need to know that. This you do. Explain what antibiotics can be used to treat bacterial infections. So look, memorize this. They inhibit essential processes in bacteria, such as disrupting their cell walls or halting reproduction. This leads to the bacteria being destroyed or their growth and reproduction being stopped. And antibiotics specifically target bacteria. They do not damage human cells. So why are antibiotics used to treat bacterial infections? Because that's a massive one. They do not damage human cells, they only damage bacteria. And antibiotics inhibit essential processes in the bacteria. Okay, because of time, I'm now just going to, there's only a few topics from triple I'm going to have to miss, which is 5.17. If there's a little bit of time at the end, I will come back to it. 5.17, 5.18, which is investigate the effects of antiseptics, antibiotics, or plant extracts on microbial. So this is all linked to core 5.17, 18, 19 are linked to core practical. So I would advise watching one of the Edexcel based videos on YouTube. And this is using pi r squared to work out the inhibition zone around when doing the actual practical. So here you can see the inhibition zone. So you just do pi r squared and you can work out the inhibition zone. Okay, 5.20. So 5.17, 18 and 19, I know I've skipped them due to time constraints, but if you watch the recording that's been made by Edexcel Pearson, it does cover everything in a lot of detail. They are very, very good videos. It's better than just going through the theory. So there's different stages of developing new drugs. There's the discovery phase, development, preclinical, then there's phase 1, 2, 3 clinical trials, and then there's the peer review. So it's important to understand what happens at each stage. The first stage is discovery, and that's where scientists identify potential substances that could be used as medicines. For example, penicillin was discovered in mold, while other antibiotics have been developed by studying soil bacteria. And then we've got development. So once a promising substance is identified, it moves to development stage. Now they may modify its chemical structure to improve its action, or make it easier to deliver in the form like a tablet, an injection or a spray. So in development phase, they start to make the actual medicine. Now that they've made the medicine, they need to see if it works. So the first thing is preclinical trials, which is where they, before using it on humans, they test it on cells, tissues, to see if it's toxic or not, and then they try it on small animals, on whole, to see how safe it is and how effective it is on small animals and slightly medium or larger animals. Then we move on to the phase 1, 2 and 3 clinical trials. This is where they start to use human beings. So initially they test it on a small number of healthy individuals. Why do they test on healthy individuals? Because it's too risky to use it on an ill person. And this is to test toxicity, side effects, and how the body is going to process it. Initially they only used low doses just for safety, and then it slowly increased. Then they use a small number of actual patients. Then that's to find the optimum dose, to see if the drug works, and then to check for side effects. Now this whole part is done as a double-blind study. That means one group is given a placebo, which doesn't contain the medicine, and the other group is given the real drug. Now no one knows who's been given what. That means group 1 and group 2, they don't know if they've got placebo or the real thing, and even the doctors and the researchers don't know who's got what. So that ensures that no one's messing around with the results. Okay, and finally it's done with a large number of patients for the same reason, to find the optimum dose, to see if the drug works. And again, it's done as a double-blind study to avoid any bias. Now, placebo is just a medicine that tastes similar to the medicine, so that it's actually not a medicine. It's just something given. It's just designed to resemble the real drug. That way, people think they've actually been given the medicine when they haven't, and then they have a comparison. So if one group starts to get better and the other one doesn't get better, then they know the medicine's actually worked. Sometimes when a person takes medicine, when someone takes medicine, it does lead to it leads to positivity, and then they wouldn't know if it was because the person's just felt better, they've been exercising more, there's a change in the lifestyle because the medicine has had a positive impact, or is it the actual medicine that's done the change? Okay, 5.21. Now, monoclonal antibodies, if you just excuse me 1 second, this should be a triple award content, but there was no letter B there, so I'm just going to quickly check, because I do not remember this being a combined topic. So just bear with me for 1 second. Well, not for 1 second, give me at least 10. Yeah, 2-1 and 2-2 are triple award. Right, so I'm going to just, with monoclonal antibodies, I'm just going to very quickly explain how they're made. Then we'll move on to 2.2 and 2.3. Now, this mouse is injected with an illness. Then the body starts to make the antibody, the monoclonal antibody that kills off so the white blood cells, the lymphocytes, that would defend it against that particular antigen. So what they're doing is, here's a bacterial cell, the antigen is the protein group. They inject the antigen, the protein groups, into the mouse. The mouse then produces the desired antibody. That cell that has the antibody inside it is mixed, as in it's in a sense they combined with the tumor cell. Now, tumor cell rapidly divides, and this plasma cell contains the antibody. So now we have a hybridoma cell that, like the tumor cell, rapidly divides, and like the plasma cell, has the antibodies. And once the cell part is separate, so that means it now starts rapidly multiplying and producing lots and lots of antibody. Then the antibodies are separated from the rest of the cell, and they can be used for many things. So the mouse is injected with the antigen that we want to create antibodies against. This stimulates the mouse's immune system to produce the lymphocytes, the white blood cells that generate the desired antibody. These lymphocytes are then removed, and they're fused with a type of cancer cell, one of the rapidly dividing ones, and that makes a hybridoma cell. These cancer cells are chosen because they divide rapidly, and that solves the problem because lymphocytes don't divide. They're made from stem cells. So this new cell we call a hybridoma cell that then divides rapidly like a cancer cell and produces the desired antibody like the lymphocyte. So now, as the hybridoma cells divide, they produce large quantities of identical or monoclonal antibodies. These antibodies are then harvested and purified. Okay, now they have lots and lots of uses, like in cancer therapy and in pregnancy tests. So this is a really good question and answer that I would advise anyone that's doing triple to spend a bit of time and go through. So describe how a pregnancy test uses monoclonal antibodies to show that a woman is pregnant. So the thing that the monoclonal antibody actually attaches to, the pregnancy test detects a specific hormone in a woman's urine, such as HCG. The hormone binds to a monoclonal antibody on a test strip, and they're complementary to the hormone HCG. These antibodies are attached to a coloured bead or tag. As the hormone antibody complex moves along the strip, it reaches these immobilized antibodies. So there's more antibodies. So now we've got antibody that's attached to the HCG, and this has like a what does it say? How does it say here? Like a coloured bead or tag. Now, as it attaches to this more immobilized phase, and they attach here, then these coloured beads come into a line like this, and you can see that line on the pregnancy test. Okay, 5.23. Describe that many non-communicable human diseases are caused by the interaction of many factors. So this is what we've already covered, but that was from a communicable perspective. But this is just saying that a non-communicable disease is a disease that cannot be spread from person to person. It is usually caused by genetics, lifestyle, or environmental factors. Now when we covered this before, we were referring to communicable diseases, that you can get a communicable disease and that can cause other illnesses. So HIV can lead to tuberculosis. Now we're looking at how non-communicable disease can also do this, a similar thing. So these are examples of non-communicable diseases. Cardiovascular disease refers to a group of conditions that affect the heart and blood vessels. It is usually caused by a buildup of fatty deposits in the artery which can narrow or block them. So what is cardiovascular disease? The coronary arteries get narrower, fat builds up inside the arteries, making them tighter. So now the coronary artery is the artery that feeds our heart. It's the artery that takes oxygenated blood to the heart. So if that one gets blocked up, then that is a heart attack. So less blood flows through the artery. The narrowing blocks the normal flow of blood. That means we have less oxygen reaching the cells. Less respiration happens because without oxygen there's no respiration, and that means without respiration it means an individual will have less energy. Okay, cancer, another type of non-communicable disease. Cancer is an uncontrolled growth and division of abnormal cells in the body. So this is something we've already covered. And then there's examples of liver and lung disease. So diet, stress and life situations all affect a person's health. Pathogens, harmful microbes, can cause immune reactions which may lead to allergies like skin rashes or asthma. Serious physical illnesses can lead to mental health problems such as depression. A weak immune system can make a person more likely to get infections, and there's some viruses that live inside cells that can trigger cancer as well. Okay, explain the effect of lifestyle factors on non-communicable diseases at local, national and global levels, including exercise and diet on obesity and malnutrition, including BMI and waist to hip calculations, alcohol and liver disease, and smoking on cardiac. The main thing we're going to focus on is this BMI and waist to hip calculations. So how do we calculate the BMI? So this is the body mass index, and this is a maths question that can come up in an exam. So BMI, the body mass index, equals the mass of a person in kilograms divided by the person's height, but squared. Now a lot of people, same as in physics, when we've got kinetic energy equals half mv squared, people forget to square. The same thing happens in biology and this one particular topic. So make sure you don't forget to square. And depending on what your result is, between 18.5 to 24.9 is normal BMI. And as you get, the BMI gets higher and higher, it shows obesity and extreme obesity. Now, generally speaking, if a person has a higher BMI than 25, the higher it goes, the more likely it is that a person will have issues like cardiovascular illnesses and blood pressure problems and things like diabetes. So we know how to calculate it. So what is the BMI of a person who weighs 70 kilograms and is 1.75 meters tall? So step 1, get the data. Step 2, add it into the formula and then just calculate. So we're going to do 70 divided by 1.75 squared, and that equals 22.9. So this person has a normal ranged BMI. Now the issue, and what impact will that have on diet and exercise, on obesity? So a poor diet and a lack of exercise can lead to obesity. obese people are more likely to have cardiovascular disease or diabetes. A person that drinks a lot of alcohol, now so we're looking at the impact of diet and exercise on obesity. So alcohol can damage the liver and affect brain function. Smoking can increase the risk of lung cancer, lung disease and cardiovascular disease. So what we're looking at, rather than that as a title, we're just looking at different lifestyle factors and what impact they have on health. Now this is a common thing to be asked questions on too. Okay, thank you very much. That is the end of the biology part of the AMALathon. So we're going to take a 4-minute break and we will recontinue at 2:40. Okay, welcome back everyone. Now, I did say we're going to start from 3.25, but I'm actually going to go to 3.26 first and then go back to 3.25, and it will make sense as I start. So, I just want to explain a couple of things. If you have sodium chloride, so as a solid, it's going to be positive and negative ions with lots and lots of electrostatic attraction between them. So it's got a very high melting or boiling point because of the attraction between all the positive and negative ions. Now there's two ways we can get this to conduct electricity, because as a solid, the ion's not free to move. The first method is you melt it, or you bring it to the molten state. Meaning, if this is sodium chloride liquid, then the only thing in here is the positive and negative ions from sodium chloride. But now we've heated it up to such a high temperature that there's enough energy for them to break free from the electrostatic charge attraction. Now it will conduct electricity. So in electrolysis, the ions are free to move, so this can be used for electrolysis. But what's the only thing in here? The only thing in here is Na plus and is Cl minus. Now the other thing that can happen is added to water, and the Na plus and Cl minus separate from each other. So we have Na plus and we've got Cl minus, and they dissociate, they break apart. So now what we've got is Na plus, we've got Cl minus, but we've also got water. And the water also dissociates, particularly when electricity flows through it. It breaks up into H plus, let's put it over here, H plus and OH minus. Now, when we do electrolysis, what you've got to keep in mind is that when you add your electrodes, you have your positive anode, positive electrode, and you've got your negative electrode. Now if we look at this example here first, the only thing is we only have Na plus and we only have Cl minus. And what that means is all the Na plus is going to go to the cathode. Remember, panic. Positive anode, negative is the cathode. And where are all the negative chloride ions going to go? They're going to go to the anode. So there's only two ions there. So we know which ion is going to go to the positive, and we know which ion is going to go to the negative. But when you do electrolysis within a solution means it's been dissolved in water. Now we have an option. So we need to find out which one, Na plus or H plus, which one is going to form here at the anode. I mean at the cathode. Is it going to be Na plus or is it going to be OH minus? And with Cl minus and OH minus, which one is it going to be that forms at the positive anode? So for these, there's rules. So this comes under 3.25 and we need to learn those rules so we know what's being made at the anode and what's being made at the cathode. For this one, it's a lot more straightforward, which is why I'm going to go 3.26 first. So I'm going to just erase all this out. So the example that's being given in front of you now says if you've got lead bromide. So our electrolyte is lead bromide. So what's the only thing inside our electrolyte? We have got lead, and the only other thing we have is bromine. So the only ions in that electrolyte are lead, positive ions, and bromine, negative ions. So what that actually means is the bromine is going to be attracted to this positive anode, and bromine will form here as Br2. And what bromine actually does is this. Br minus, when it goes to the anode, it gives its electrons to the anode. So 2 bromine minus becomes Br2, and it's given away its electrons, so it's lost 2 electrons. In other words, if it lost electrons, it has been oxidized. Now the lead goes to the negative cathode. Remember, panic, positive anode, negative is the cathode. Which means, let's show it over here, Pb2 plus, it goes to the negative electrode here, the cathode, and it gains electrons. To become just lead. And that lead will start attaching itself to this electrode. So the products from this type of electrolysis, so remember this electrolysis, what's the electrolysis of? When something is molten. So it's the electrolysis of molten ionic compound. So if you've got zinc chloride, what's the zinc chloride going to, what product are you going to get from zinc chloride? Well, always the metal will form at the cathode, and the non-metal always forms at the anode. So what we're going to get is the zinc and chlorine. What will we get from lithium oxide? Lithium and oxygen. Because in the solution, there's nothing else there. So the electrolysis is of molten ionic compounds. It's the molten version of lithium oxide, meaning there's nothing in that liquid other than lithium plus and oxygen 2 minus. What about potassium fluoride? So that's going to make potassium and fluorine. Copper oxide, copper and oxygen. Sodium chloride. At the negative electrode, the cathode, we're going to get sodium. At the positive anode, we're going to get chlorine. And this is what this takes us back to. If anyone's unsure of why it's positive and negative, you need to go back to our topic 1 lessons. Because remember, if you think back, and I hope you remember this, for example, with sodium chloride, let's use that as an example. Sodium has 1 electron in the outer shell. Chlorine has 7 electrons in the outer shell. And what does sodium do? It gives its electron to chlorine. So sodium loses an electron and becomes Na+. Chlorine gains electron and becomes Cl-. So the positive Na+ is going to go to the cathode, which is negative. And the negative chloride is going to go to the anode, which is positive. Okay, now let's look at the other electrolysis, which we were just discussing yesterday. So what we've got, let's use NaCl as an example. We've got Na+. No, sorry, let's just have NaCl. And we've got our 2 electrodes. We've got our positive electrode. Which one is a positive electrode? Panic. Positive anode, so this is our anode. And over here, we've got our cathode. So now that we've got our cathode, we've got Na, so from NaCl, we've got Na plus and Cl minus. But this is a solution, it's an aqueous solution that the sodium chloride has been dissolved in water. So because it's been dissolved in water, when the electricity goes through it, the water dissociates and breaks apart too. So the H2O breaks into H plus and OH minus. Now the issue we have in this case is we have got more than one positive and more than one negative ion. So which one forms here and which one forms here? So let's look at the positive. Let's look at the cathode first. So here we've got H plus and we've got Na plus. But which one forms? Now the rule is the least reactive positive ion gets discharged. So out of sodium and hydrogen, which one is the least positive? The least positive is the hydrogen. So what forms here is hydrogen. Now at the positive electrode, we've got Cl minus and we've got OH minus. And what's the rule at the anode? If a halide ion, Cl minus, Br minus, I minus is present, it is discharged as a halogen gas, chlorine, bromine, iodine. So Cl2, Br2 or I2. Now if there's no group 7 ion, then what's discharged instead? Oxygen is discharged, because what reacts there is the OH minus ions. So what actually happens is, I'll show you the half equation in a second. Okay, so in this case now, which we do have, so look, follow the rules. If a halide ion is present, then it's a halogen which is made, so something from group 7. If there's nothing from group 7, then oxygen is released because it's the OH minus that reacts, that is discharged. So in this case we do have a Cl minus, so it's the Cl minus that will be discharged. Now let's look at the products. Let's go through a few examples here. Let's go through the top one first. Copper chloride. Now from the copper chloride, let's have a look at it over here. We've got copper 2 plus, and we've got Cl minus, and because it's a solution, we've got H plus, and we've got OH minus. So now we've got to work out what's going to form at each one. So at the cathode, the rule is, the one that is the least reactive. So in this case, copper is the least reactive. So copper will be discharged. It says it here because copper is less reactive than hydrogen. Now, from chlorine Cl minus, a chloride ion, and OH minus ion, which one's going to be discharged? And the rule at the anode is group 7, and if there's not group 7, then it's OH minus. But we have a group 7 there. So then it'll be the Cl minus that's discharged. Now let's look at lithium oxide. Lithium, so this time round we've got, let's do it over here. We've got Li plus, and oxide is oxygen, so that's O2 minus. Alongside that we've got H plus from the water and OH minus. Now the rule is, first it has to come from we're looking at the positives first. It's the least reactive that goes first. So which one's less reactive? It is the hydrogen that's least reactive, so we get rid of the lithium. And the rule at the anode from the negative ions is, if it's the one that won't react, if it's first, the rule is either it's a halogen, so halide ion, there's no halide ions there, so then what's discharged is the OH minus. Now what I'm going to very quickly show you is how to write half equations for this. It's going to be the next topic anyway, but if I explain it with this context, it makes it easier. So let's look at copper 2 plus first. Now what the copper 2 plus will do, it will go to the negative cathode and it will gain 2 electrons from the cathode to become copper. The Cl minus, now there has to be 2 of them because they make Cl2. Now what's happened to those negative electrons, so it can become neutral? It's lost those electrons, so it loses the electron. We always show loss of electrons on the product side. So here copper 2 plus has been reduced because it's gained electrons, and on the second one the chlorine ion has been the Cl minus has been oxidized, so that's a redox. So all of these electrolysis reactions are redox reactions. Okay, now let's look at the H plus and the OH minus. Now there's one of these reactions you will need to memorize. The rest you can understand. I mean, if you if you end up knowing, understanding it and not having to memorize, that's even better, but we'll go through it. So with lithium oxide, we know hydrogen gas is produced. So that means H plus, it goes to the cathode, and what does it get from the cathode? So what you've got to remember is at the cathode, we always gain electrons. It's always reduction. At the anode, at the positive anode, we always lose electrons. So oxidation. So 2H plus gains 2 electrons. Now it's 2H plus because hydrogen exists diatomically as H2. Now the half equation for OH is like this. So we have 4OH minus becomes oxygen plus 2H2O plus 4 electrons. So it loses those electrons. Now that's the half equation. Every single time it says oxygen gas. So all of these would have this half equation to show that oxygen gas is discharged. So this is what I've just explained. So I'll go through it slowly, so afterwards you can still read through it yourself. Now, if something loses electrons, then that's oxidation. If something gains electrons, that's reduction. Okay, so finally this is linked to the required practical. So I'm going to go through the theory, but I advise that you watch the video from Pearson Edexcel so you can see it actually happening. How can copper be purified with electrolysis? So a direct electric current is passed through copper sulfate solution. So what we've got, our electrolyte is copper sulfate, meaning we've got copper 2 plus, SO4 2 minus. Now what else do we have other than SO4 2 minus? We've also got H plus and OH minus. That means the copper 2 plus and the OH minus are the ones that were discharged. So we're going to get copper 2 plus at one electrode and we're going to get oxygen at the other electrode. So now a direct current is passed through copper sulfate solution. The anode is made of impure copper. So when we say anode, remember panic. So the anode is made of impure copper. So that's where the oxygen is being discharged. While the cathode is made of pure copper, and pure copper is made at the cathode. So what happens here is, here we've got, a negative cathode, we've got a positive anode, now in here we've got copper 2 plus, and when that copper 2 plus goes to the cathode, the copper 2 plus gains electrons. And when it gains those 2 electrons, it becomes pure copper. So what happens at the cathode and the anode? So at the positive anode, the copper atoms become cations and dissolve. So what happens is the copper, so remember this is the impure copper. It breaks apart, the copper inside there, the impure part, it becomes copper 2 plus. So it adds copper 2 plus into the electrolyte. At the negative electrode, the cathode, the same copper 2 plus, the copper 2 plus that's in the electrolyte, it gains electrons and attaches itself onto there as copper. So let me just explain that one more time. But it's easier to also explain in the reverse. So what's happening here is we've got an electrolyte in here, which is copper sulfate. So we've got copper 2 plus already in there. Where does the copper 2 plus go? It goes to the negative cathode, it gains 2 electrons and it attaches the copper onto the electrode, the pure copper. That means from the electrolyte, copper 2 plus has been taken out. But at the same time, what's happening in the impure copper is that copper is breaking down into copper 2 plus and 2 electrons. So that's releasing copper 2 plus into the electrolyte. That means the amount of copper 2 plus in the electrolyte doesn't decrease or increase. And it keeps from the impure copper, the impure copper electrode keeps replenishing the copper 2 plus, and then that copper 2 plus keeps attaching to the pure copper electrode. So it keeps building a layer on the other side. Okay, now this is the core practical, which I advise you watch using the Pearson Edexcel website. Okay, that's the end of topic 3. If anyone has any questions, you are more than welcome to ask. Please keep asking questions if something doesn't make sense. And I'll do my best to answer questions live. Okay, so let's move on to topic 4, chemistry. So let's get started. Okay, so after we've completed topic 4 chemistry, then we will be moving on to topic 6 physics, and that's where we're going to be finishing our session today. Topic 6 physics. That means the only one that we won't have completed is unfortunately topic 5, but we have still managed to get through quite a lot. I have gone through things a little bit faster towards the end, but of course you can watch the recording goes straight onto YouTube, so you can always watch it back and go through things at your own pace. Now, a lot of what, for example, biology topic 1 will also come in the paper 2 exam, and I took quite a bit of time on that. And chemistry topic 1 also will come in the paper 2 exam, which is why I took my time with that also. We spent 3 lessons on chemistry topic 1 because it really is a foundation topic. Okay, so deducing reactivity. So how can we deduce determine the order of elements in the reactivity series? So in the reactivity series, if you look at it, potassium is group 1, sodium is group 1, lithium is group 1, calcium group 2, magnesium group 2, aluminium group 3. So generally speaking, group 1, 2 and 3, well, particularly aluminium from group 3, but definitely group 1 and 2, are more reactive than carbon. Then what you've got after carbon is transition metals like zinc, iron, tin, lead. And then you've got hydrogen, then you've got copper, and then you've got things like silver and gold, which are very unreactive. So unreactive that you find them pure in mountains. Now, how can you determine the order of reactivity? You add these metals to water or undilute acids as separate experiments to see what the temperature change is. So here you've got a spatula. You take the metal, you add it to the water, and then you determine the temperature change. You would do that 3 times, remove any anomalous results, and then do the same thing with water and keep a recording of the temperature changes, and that will give you an understanding of which one is the most reactive. Now, what happens when substances in this reactivity series react? So a more reactive metal can take the place of a less reactive metal in a compound. So if you're reacting, for example, iron sulfate and zinc. Now let's have a look what iron and zinc are. Ooh, there's zinc, there's iron. Zinc is much more well, not much more, it's only a little bit more reactive, but it is more reactive. So what zinc does is, it says, I'm stronger than you, iron, and takes the sulfate from it. So what we're left with is, because the zinc has taken the sulfate from the iron is now just pure iron, and we've got zinc sulfate. Because why does the zinc sulfate why has the zinc taken sulfate? Because it is more reactive. So it's almost looking at it as though to say it is stronger. So it displaces the iron. Okay, now this is a redox reaction as well. Now I'm going to very quickly explain how it's a redox reaction. Particularly for those that are doing triple award and those doing higher, it's important that you can break this down into a redox reaction. So we've got iron, which is Fe2+. How do we know it's Fe2+ though? We know because sulfate is SO4 2-. That means iron has to be Fe2+ to balance it out. Then we've got zinc. Now what's the charge of zinc? Nothing. Why is it nothing? Because it's an element, and that becomes iron, which doesn't have a charge. Zinc, in this case, is zinc 2+, and we've got SO4 2-. Now what I'm going to do is I'm going to erase the ones that didn't change. So we've got SO4 2- here, and it's also SO4 2- here. So we're going to delete, that's a spectator ion. Now let's quickly write up our half equations. So we're looking at one element and its ion. So Fe and its ion Fe2+. So we've got Fe2+, and it becomes Fe. Now what has to change in Fe2+ for it to become Fe? It has to gain 2 electrons to get rid of that positive charge. So now that means Fe2+ has been reduced. Let's look at zinc now. We've got zinc, and zinc becomes Zn2+. Now what does zinc have to do to become positive? What do all metals have to do to become positive? They have to gain electrons. Sorry, they have to lose electrons. So in this case, the zinc loses the 2 electrons. So that means the zinc has been oxidized. So we all know displacement reaction is where a more reactive element displaces, pushes out a less reactive element. So oxidation is loss of electrons and reduction is gain in electrons. During a displacement reaction, both oxidation and reduction happen. So that's a redox reaction. Okay, these are just examples for you to look at of where displacement reactions have or have not happened. Okay, now I've gone through one example already, but I'll go through this one as well. So we've got what's happened in terms of ions during a displacement reaction. So let's explain again why this is a redox reaction. So in copper sulfate, we've got copper 2 plus and SO4 2 minus, except this time it's reacted with magnesium. Now magnesium is an element, that's where we only write Mg. Then we've got magnesium sulfate. Now magnesium is in group 2. This in group 2, because it's in group 2, it's going to be Mg2 plus. And the sulfate part is SO4 2 minus. And copper is an element, so do elements have a charge? No, because the positive and negative, the number of electrons and protons is balanced. So the first thing we do is we delete the spectator ion. That's the one that doesn't change. So again, it's sulfate, SO4 2 minus. Now we're going to look at each element and ion one at a time. So let's look at copper 2 plus first. Copper 2 plus becomes copper. What does the copper 2 plus need to do to become just copper? It needs to gain 2 electrons. So the copper 2 plus has been reduced. Then we've got magnesium, so we've done copper now. Now let's look at magnesium. Magnesium on the left hand side. On the right hand side we've got Mg2 plus. Why does the Mg2, what does the magnesium need to do to become Mg2 plus? What do all metals have to do to become positive? What do humans have to do to become positive? They've got to lose their negativity. They've got to lose their electrons. So the magnesium loses electrons. So you could put it as this, minus 2 electrons. Now, from an algebra perspective, if it's minus on one side, what will it be on the other side? It's going to be plus on the other side. So now the magnesium has been oxidized because it has lost its electrons. So this is high level stuff. This is the stuff that students in doing higher, doing triple, the ones that get grade 9s, they've mastered this. Okay, now we've already mentioned what the reactivity series is. It's just a list of going from the most reactive to the least reactive. And it includes carbon and it includes hydrogen as well as a comparative. Now, the more reactive a metal is, the more likely it is to displace. The more likely it is to displace a less reactive metal. So more reactive will displace a less reactive. Okay, extracting metals. Now, something like silver and gold is found pure. Anything that's less reactive than carbon, we do a displacement reaction. And by that I mean we react it with carbon, and because carbon is more reactive than zinc, iron, tin, lead, copper, if you've got zinc oxide, iron oxide, tin oxide, lead oxide, copper oxide, the carbon will displace the metal. So we can reduce it with, or reduction with carbon. The carbon will take the oxygen from it. That's what we call it, reduction. And anything that's more reactive than carbon, you won't get a reaction if you react it with carbon, so instead you have to use electrolysis. So, when a metal reacts with oxygen, it becomes a metal oxide. In other words, it has been oxidized. So if something gains an oxygen, we say it's been oxidized. Another way of saying oxidation is loss of electrons. So it's a gain of oxygen, but the loss of electrons. So oxidation is when a substance gains oxygen, but it is a loss of electrons. But reduction is when a substance loses oxygen, but it's a gain of electrons. So, how are metals extracted from the ores? So what we do when we're talking about these metals here, what happens to the ones more reactive than carbon? We use electrolysis. But if they're less reactive than carbon, then what we can do, some metals can be taken out of the ores by heating them with carbon. So it's called reduction with carbon. Carbon's not a metal, but it fits in the reactivity series between aluminium and zinc. It's also quite cheap compared to using another metal to make a pure metal. So if I had iron oxide, I could react it with zinc, and the zinc would make it pure iron, but then I'd have zinc oxide, and it'd be a waste of money. So if it's more reactive, we use electrolysis. If it's less reactive, then we heat it up with some carbon, and the carbon takes away the oxygen, so it becomes carbon dioxide, and you're left with a pure metal. So if you've got, for example, zinc oxide, if you react it with carbon, this is not balanced, by the way, it'll make carbon dioxide plus zinc. Like I said, I've not made it a balanced equation. I don't have to do too much to make it balanced. So there's the same example, zinc oxide plus carbon. The carbon displaces the zinc and it replaces it. So then we're just left with zinc. Carbon is stronger than zinc, so it pushes the zinc out of its compound. It displaces it. Zinc is reduced because it has lost oxygen, which means it has gained electrons. And carbon is oxidized because it takes the oxygen, which means it has lost its electrons. So what you now, if you were asked to turn this into a symbol equation, what you would do is look at oxygen. Oxygen is in group 6. If it's in group 6, it's got 6 electrons in the outer shell. 6, and it's going to gain 2 more for a full outer electron shell, so it becomes O2 minus. That means zinc must be Zn2 plus. Now, how many 2 pluses can cancel out 2 minus? Now all you've got to do is cancel them out. So that's just a 1-to-1. We need 1 zinc to cancel out O2 minus. So that means the formula will be ZnO. Now if we had aluminium oxide, aluminium is from group 3, it loses 3 electrons. So it's Al3 plus. And so let's say we made aluminium chloride, and chlorine is Cl minus. Now if that's a 3 plus and that's a minus, just make that to an equal sign, let me just hold that out, and that's a minus, how many of those minuses do we need to balance out the 3 plus? We need 3 of them. So we need 3 Cl minuses. So its symbol equation, its formula for aluminium chloride is AlCl3. Now there's another way of doing this, which is what's shown on this PowerPoint, is, and some of you might prefer this, aluminium, chlorine, that's 3 plus, that's minus 1, just swap the numbers, put that number there and put that number there. So we've got Al1 Cl3, whatever works. So here's some examples. Iron oxide plus carbon. What does the carbon do to the iron? It displaces it to leave iron plus carbon dioxide. And there's a symbol equation. Here we've got copper oxide plus carbon. What does the carbon do? It displaces the copper. So we've got, in the end, we have copper and copper oxide. So these are examples that I would go through, make sure you properly understand them. Now, metals can be removed from the molten compounds using electrolysis. When do we use electrolysis? When the metal is too reactive for it to be taken out using carbon. So if it is more reactive than carbon, we can't use reduction with carbon. We have to use electrolysis instead. But a lot of energy is used in this process to melt the compounds and to create the electrical current. This is what we already have covered, but we'll quickly go through it. Aluminium is made using electrolysis of molten aluminium oxide. So here we've got molten aluminium oxide, Al2O3. And what we can't do is add carbon. Now the aluminium oxide is mixed with cryolite. Cryolite is a catalyst. So it lowers the melting point of the aluminium oxide. In other words, it speeds up the rate of reaction without becoming part of the reaction. And part of what it does is it lowers the melting point needed. So it lowers the temperature needed to melt aluminium oxide, and that saves energy and reduces costs. The positive electrode is made of carbon, made of graphite specifically. The aluminium oxide ions, because they're Al3+, they go to the cathode, and when they go to the cathode, they gain 3 electrons and become aluminium. Remember, the cathode is negative. Okay, so this is what we've already covered in electrolysis, so we are going to move on quickly. So we're going to move past the electrolysis section. Okay, biological metals, biological methods. So, how can metal be extracted from low-grade ores? So usually if a company drills into a mountain, when a company drills into a mountain, what they find in the mountain is rocks. And if the rock has enough of the metal inside, so usually if it is, for example, if it's red, that's an indicator that it's got iron inside it. If it's like a bluish colour, it's indicated it's got copper. Different colours indicate different metals. Now if it has enough of the metal inside, then it's called what we call an ore, a high-grade ore, meaning a lot of money is going to be made from it. Whereas if you get one that only has a hint of the metal, then that would be classed as a low-grade ore, and that'll just be discarded to one side. But now we're at a point where the Earth's supply of metal ores are running out, so they're looking for new methods, and we've got a couple of biological methods here called phytoextraction and bioleaching. So what happens during phytoextraction or phytomining? So what happens is they use plants to take in the metal compound from the soil, meaning the plant grows, it's got roots, and due to active transport and diffusion, the copper enters then it goes into the plant and it's stored in the plant. And once it's stored in the plant, the plant is then burned. Afterwards, apologies, I'm having definitely some sort of connectivity issue going on. Alright, stop now. So the plants are then collected, and if they have a little bit of copper inside them, they're burned. And what that leaves behind is ash. And what they do with the ash is they add it to sulfuric acid. Now when the ash when the ash reacts with when the ash reacts with sulfuric acid, it makes copper sulfate or metal sulfate, but in this case copper sulfate. Then they use electrolysis on the copper sulfate to purify the copper. Now bioleaching is a little bit different. Apologies, I'm not sure. There's a little bit of a technical issue at the moment. Hopefully it's sorted itself out now. That's good. Okay, now bioleaching is using bacteria. No, apologies, my pen stopped working. It's fine, I'm just going to have to explain things then. Bioleaching using bacteria to break down low-grade ores. And that creates a solution with, so if you look at my arrow, a solution with copper ions. That's called a leachate or leachate. Now, what we've kind of formed, that means when we're using phytoextraction, we end up with copper sulfate solution because we take the burnt ash and we add it to sulfuric acid. Now, so we end up with a solution of copper sulfate. With bioleaching, we end up with a leachate, which is full of copper ions as well. So then what has to happen after that is they use electrolysis to then extract the pure metal. So this is what we looked at in topic 3.30. So if you go back to what we covered in 3.30 in chemistry, 3.30, this will explain what's happening in this process. And that produces copper. Now, this is a positive thing because it avoids digging, moving and throwing away large amounts of rock. It helps save the limited supply of high metal ores. However, there are downsides because bioleaching can create toxic substances that harm the environment. One half of the substance made is sulfuric acid, and if you've got a big field of plants and then you're burning them just to get a little bit of copper, that's a waste of a big field. It could be used to make food. Okay, position in the reactivity series. What is the reactivity series? So we've covered this already. When metals react, they form positive ions. They're more easily a metal forms a positive ion, the more reactive it is. So it's something we'll cover in topic 6 chemistry. That as you go down group 1, it becomes easier and easier for the electron to be removed, for it to lose the electron. The easier it is for it to lose that electron, the more reactive it is. Okay, recycling. So this is life cycle assessments, LCAs. Metals can be recycled by melting them down and reshaping them into new products. So metals can be recycled. The amount of sorting needed for recycling depends on the material and the final product. The amount of sorting needed for recycling depends on the material and the final product's required properties. For example, scrap steel can be added to iron in a blast furnace. This reduces the need to extract more iron from an iron ore. So what are life cycle assessments? So all this 4.10, the kind of questions you get on this is more data-based questions, less to do with any memorization. So this comes from past paper practice. So life cycle assessments. Life cycle assessments check how products affect the environment at each stage. So we are going to go through an example question, and that will put a lot of it into context. Now, what are the different parts of a life cycle of a product to consider? So one is getting and processing raw materials. So lots of different things to consider. So for example, if you have a carrier bag that's made of plastic, life cycle assessments. And if you've got if you've got a bag made of plastic, you've got a bag made of paper, life cycle assessments looks at things like where the raw material is coming from, how strong is it, the design of it, how functional is it? So how easily is it made and packaged? How long does it last for? So it considers all these different things from an environmental impact perspective, sustainability perspective. So things to consider is how easily is it disposed of at the end of its life. So let's just start this again so you can see all of them. So when we're looking at a product, we're considering how easy is it to get hold of and to process the raw materials. So to make a carrier bag, you've got to use crude oil, which is a topic that Year 11 should have covered by now, which kind of adds a bit of context to this. How easily is it made, packaged, using the product during its lifetime, how long does it last for? At the end of its life, how easily is it disposed? How long does it persist in the environment for? The transport and distribution at each stage. Now we can measure the use of water, resources, energy, and the waste products made from it quite easily. However, giving numbers to pollution effects is harder, and that involves opinions. This means LCAs are not completely objective. So some LCAs are shortened or selective to evaluate a product, but they can be misused. They might be designed to support pre-planned conclusions, such as making a product look better for advertising. So sometimes an LCA can manipulate, companies can use LCAs to manipulate the data to make themselves seem more eco-friendly than they actually are, is what that means. Now, how are they completed? So we've got an example here. We've got a plastic bag versus a paper bag. So the raw material for a plastic bag is crude oil or natural gas. So let's go through one thing at a time. So exam questions often ask you to evaluate. So again, this whole topic and recycling as well, 4.10, 11, 12, usually you're asked evaluative questions. So you've got to know how to evaluate more than anything else. So the exam questions often ask you to evaluate. So let's go through a comparative. So to answer this type of question, you look at each factor and then you compare the materials. Use your own knowledge, don't just copy the data. So don't just say, energy used, the paper bag uses more energy. Solid waste, the paper bag's got more solid waste. Carbon dioxide production, the paper bag's got more carbon dioxide production. The water used, the paper bag uses more water. And go, yep, I'm done. Evaluation finished. It has to add your own explanation to it. And you need a justified conclusion at the end based on your comparison. So when you're evaluating, you're looking at the data, you're giving your own knowledge about the pros and cons, positives and negatives, and then you're giving a justified conclusion. Which one do you think is therefore better? And why? So let's look at the raw materials. A plastic bag is made from crude oil or natural gas, but a paper bag is made from wood. Now, crude oil, what do we know about crude oil? It is a non-renewable resource. So eventually it's going to run out. Wood is renewable because it can be replanted. So that's a positive for the trees. For paper bags. Now, energy used Making a paper bag uses 0.2 megajoules more. So look, paper bag uses 1.7, but plastic bag only uses 1.5. Now, energy usually comes from fossil fuels, which are limited and will eventually run out. So that means to actually make that paper bag, you've got to burn fossil fuels anyway. And crude oil is a fossil fuel. The mass of solid waste. So paper bags creates 36 more grams waste than the plastic bag. The waste needs to be disposed of and can build up in landfills, causing environmental problems. But when you make the 36 grams of more waste that comes from a paper bag will more easily decompose when it enters a landfill site, whereas a plastic bag will persist for around 1,000 years. Mass of carbon dioxide. Right, that's carbon dioxide is written incorrectly. It should be written like this, as a subscript. So the paper bag releases 0.3 kilograms carbon dioxide more. Carbon dioxide does cause global warming, but when you burn a tree, it's classed as carbon neutral. The reason being, the carbon dioxide that's taken in through photosynthesis is the carbon dioxide that is released when you burn it. So that's different. The carbon dioxide that you release when you burn a plastic carrier bag is carbon dioxide from millions of years ago because it's come from crude oil. And paper bags, because at the end of the day, to make a paper bag, you have to plant trees. The trees use up a lot of water, much more water than a plastic bag. And of course, some parts of the world, because they don't have as much fresh water, and fresh water is a commodity, it's something that's going to become more and more scarce as the population increases, means it would be difficult to make a paper bag. And are you going to make a paper bag or plant trees for food? Now, how should the conclusion be structured? It just needs to be a justified conclusion, giving a statement and support it with a reason. So we've just gone through all that information. Your final statement just needs to be, I believe the paper bag would be better because it does not contribute to global warming as much as the plastic bag. Or you might say the plastic bag is better because it doesn't use up as much water and it doesn't use up as much land. Because to grow the tree, the wood, you would have to cut down. There'd be a lot of deforestation because they cut down the trees, using up a lot of water, and that land and that water could be used to grow food for people. So either way, you have a reason. Now we're looking at reversible reactions, and the last part of this is higher content, but it is all combined and triple, so everyone can be part of the viewing. Now this should take another 10-15 minutes, then we will take a 5-minute break, and then we're going to move on to topic 6, and it's the last part of topic 6, that is triple award. So we're nearly finished now with this topic, and then we're going to move on to physics. So reversible reactions can be shown as this. So A reacts with B to become C and D. Now, because it's a reversible reaction, that means C reacts with D to make A plus B. So the reaction never gets to reach its completion. It's because if you had A plus B, arrow C plus D, that would mean A and B keep reacting till A and B finish, and everything inside the container is C and D. Here, the reaction just goes on and on and on and on. So the direction of the reversible reactions can change when conditions change. What that means is you can manipulate a reversible reaction so you get more of the product. So when you heat it up or when you cool it down, that has an impact on it. And that's what we're going to be looking at in just over the next few slides, from the Chatelier's principles. Now I'm going to go through it, and my advice is memorize what I'm about to go through. The answers are always the same. So if you look through some past paper practice questions, you'll very quickly see the pattern of what the questions look like. You'll answer 2 or 3 and you say, oh, I get this now. I understand it's the same thing over and over again. So here we've got now dynamic equilibrium. So dynamic equilibrium, so a reversible reaction gives out heat in one direction, but before we start looking at this, and it takes in heat in the other direction, let's just explain this first. So if a reversible reaction gives out heat in one direction, so here is giving out heat in this direction, it's exothermic that way, but it's endothermic in the other direction. What that means is that the amount of energy is always the same in both directions. Now this is a dynamic equilibrium. So what that means is equilibrium happens when a reversible reaction takes place in a closed system, meaning no reactants or products can escape. And dynamic equilibrium is when the forward and backward reaction in a reversible reaction happen at the same time. So dynamic equilibrium, for example, is someone is going up an escalator, but they're going up the escalator the wrong way. So it's possible people have tried to do this out of temptation when they're little. They run up the escalator the wrong direction. The escalator is moving down. Now imagine that person runs up, but when they reach a certain point, they're running. The escalator is moving in the opposite direction, but they're not moving from the spot that they're in. So they're still running up as fast as they can. The escalator is still moving down, but they've reached a point that we would call equilibrium, meaning there's movement in both directions, but it's at the same rate, it's at the same speed. So when you have a reversible reaction, when we reach the point where, for example here, the hydrated copper sulfate no longer increases, but then anhydrous copper sulfate in the water also no longer increases in the amount that's being produced, then we call it dynamic equilibrium. Does that mean the reaction stopped? No, it means hydrated copper sulfate is still breaking apart to make anhydrous copper sulfate and water still reacting, they're still reacting to make more of hydrated copper sulfate. Hydrated copper sulfate is still breaking apart to make these two, and these two are still reacting to make more hydrated copper sulfate. So the reaction is still happening in both directions, but they're happening at the same rate. So we've reached dynamic equilibrium now. Neither one's going to be more than the other. So the Haber process is an example of a reversible reaction. And this is what I'm about to cover now is exactly what comes in past papers. And when you practice these past paper questions, you're going to see this is what gets covered. Now in the Haber process, you need raw materials are nitrogen and hydrogen. Hydrogen comes from natural gas, and where does nitrogen come from? It's 78% air, so it's come from the air. So I've seen questions which simply say, where do the raw materials for Haber process come from? So you say hydrogen comes from natural gas, nitrogen comes from the air. So in this reaction, the gases, nitrogen and hydrogen, are passed over an ion catalyst. So what does the catalyst do? It speeds up the reaction, but doesn't become part of the reaction. And it's done at a high temperature of about 450 degrees and a high pressure of 200 atmospheres. Now, the remaining hydrogen and nitrogen that doesn't react initially is recycled, and the whole process keeps happening. And this is and you also need to know the balanced equation. The word equation comes up in the foundation paper, but I have also seen in both papers the actual formula equation. So nitrogen reacts with hydrogen. I need to do this where there's a bit of space. I'll do it here. So nitrogen reacts with hydrogen to make NH3. Okay, and that's balanced now. Oh, I made one mistake. I'm sure some of you have spotted it. It's a reversible reaction. So nitrogen and hydrogen react together to make ammonia. Ammonia decomposes to make hydrogen and nitrogen, and that reaction is going in both directions. We have reached dynamic equilibrium when it's happening at the same rate. So our ammonia, does it increase more than what it is, and our nitrogen and hydrogen, does it increase more than what it is. Okay, now we're going to look through the dynamic equilibrium, and it's something what we call Le Chatelier's principles. Now in Edexcel you don't need to know Le Chatelier's name per se, but you do need to know the principles. Particularly, this is, I very rarely have I seen this in a foundation paper. I always see this in higher papers. When it comes up, it's one of those topics, if you've memorized it and you've done lots of past paper practice, it is straightforward. But if you have not memorized it and you've not done past paper practice, it just becomes difficult. So don't make things difficult for yourself. Do not make things difficult for yourself. Do lots of past paper practice when we finish. Everyone should remember the process by now. What's the process? You activate your brain. In other words, understand everything. Listen to all my hints in the videos. So, because I've told you which things come up, so you can memorize it. And then apply all that learning to past paper practice. And if you can do all three of those things, you have learnt enough to get yourself to a grade 9. Now, how can we activate our brain? All the AMALathon will be broken down into 6-hour videos. So all paper 1 biology will be a 6-hour video. All of paper 1 chemistry will become around 6 hours of video, and same thing for physics. So all that will be available as separate long videos, or you can just watch the whole AMALathon. One thing to keep in mind is the night before an exam is well worth watching one of these 30-minute videos that say all paper 1 covered in 30 minutes. Those are really good for last minute. But the 3 or 4 weeks or 2 weeks or 1 week before an exam, that 30-minute video is not enough to get you to a grade 9. What's good enough to get you to a grade 9 is the 6-hour video that we've made now. And then whilst you're going through that, you're memorizing, because for a lot of you that'll be the second time you've gone through it. Even if it's the first time, I'm pointing out the things that should be memorized. And then once you've gone through that phase, we apply. Now, why are we applying it to past papers? Because number one, past papers show us what past papers explain to us what we need to have, what we need to memorize. Past papers show us patterns in the questions. Past papers help us to understand the examiner's mindset. So when we read a question, we understand what the examiner wants to see. And you know, one of the most amazing things with past papers, it means you don't have to make flashcards. What's the best flashcard is where you've got a question on one side and an answer on the other side. And what is a past paper with a mark scheme? It's a flashcard. It's an automatic flashcard. And once you understand in that flashcard, if you come across something you don't know, you stop and you memorize. And that's how you get your grade 9. So it's still plenty of time. We've still got 3.5, 4 weeks. So as soon as this activate phase is finished, as soon as you've activated your brain, you've understood everything, start doing your past papers and memorizing. If you do 1 past paper a day, you will have gone through all biology, chemistry and physics, paper 1, all the past papers for paper 1 by the time, a week before your final exam. So a week before your initial biology paper 1 exam. So what we're looking at now is what is the effect of changing concentration on the rate of a reaction. So we're going to look at how temperature affects the rate of reaction. We're going to look at how concentration affects it, how pressure affects it. Now, if you increase the concentration, so if the amounts of one reactant or product changes, the system is no longer at equilibrium. The amounts of all substances will adjust until equilibrium is restored. So now if you change the equilibrium, if you mess around with that balance, everything, a part of the reaction speeds up until that balance comes back again. Now what we want to do is speed it up in this direction, so we get more product. So let's look at concentration. If the amount of product decreases, more reactants will react until more product is made, so it'll make more product till equilibrium is restored. So let's see what that means. So we've got A plus B, equilibrium, reversible reaction sign, and so it makes C plus D. So that means if I was to remove some of D, so I've reduced the concentration of D, what will happen is now we've messed around with the equilibrium. It's no longer equilibrium because we have decreased D. So the reaction going that way has slowed down. So now what will happen is A and B will increase their reaction. That reaction increases until it reaches equilibrium again. Now if the reaction increased on this side, we're going to get more C and D. So if we decrease D, we end up making, because it's at equilibrium, we end up making more C and D. Now if the amount of reactant goes up, so now if we increase A or we increase B, we've also changed the equilibrium. Now, because we've got more A and B, we've got more reaction on this side, so we end up with more C and D. So if we want more C and D, we can either decrease C and D, and that will increase the reaction on this side, or we can increase A and B, and that increases the reaction on that side as well, making more of C and D. So let's read this really quickly. If the amount of product goes down, more reactant will react to make more product until equilibrium is restored. So if we're decreasing the product, C and D, we end up making more reactants. Now if the amount of reactant goes up, more products will be made until equilibrium is reached again. Now what effect does temperature have? So look what we've got here. We've got endothermic reaction in the forward direction, and we've got exothermic in the backward direction. So we've got endo this way, and we've got exo this way. Now what we've got to remember is if we have an exothermic reaction, it's taking in heat energy. So how can we speed up a reaction that's taking heat energy in? We increase the temperature. By increasing the temperature, we're providing more heat energy. So when it's endothermic, so look here, a higher temperature helps the endothermic reaction happen more. It's because the endothermic reaction to happen, it has to take more energy in. The other benefit then is the higher temperature means the reaction happens at a faster speed because temperature increases the rate of reaction. Now an exothermic reaction is giving out heat energy. So we do the opposite. If it's giving out heat energy, we cool it down. So a lower temperature helps the exothermic reaction happen more. So if the temperature of a system at equilibrium is increased, so if the temperature increases, more product are made in the endothermic reaction. So an increase in temperature makes the equilibrium shift in the endothermic direction. So increasing the temperature would give us more anhydrous copper sulfate and water. If we lower the temperature, we would get more, it would go in the exothermic direction. So we'd get more hydrated. If the temperature decreases, fewer products are made in the endothermic reaction. If the temperature decreases, more products are made in the exothermic reaction, meaning you get more of the hydrated sulfate. Now what effect does copper have? Whoops. Now, when you increase the pressure, it always goes in the direction where there's fewer molecules. So here we've got 1, 2. On the product side, we only have 1. So if you increase the pressure, the equilibrium moves to the side with fewer molecules. In other words, we get more of C. If the pressure decreases, the equilibrium moves to the side with more molecules. So it goes, it means we end up with more A and B. Now, there will be no change this reaction. So if we increase the pressure here, you've got 2 on the left hand side, you've got 2 on the right hand side. So because you've got the same number of molecules on both sides, increasing the pressure has no overall impact on the equilibrium. It only goes in the direction where there's fewer molecules. And pressure will only affect an equilibrium if gases are involved. And also if there's different number of particles on each side of the equation. So here, nothing happens. It won't have an impact. Okay, thank you everyone. That is the end of chemistry. So we're going to continue at 4 o'clock. So we've now finished our biology AMALathon. We finished our chemistry AMALathon. Just topic 6 to go. So I'll see you guys in a few minutes. Thank you everyone. Okay, welcome back everyone. It's our final part of the AMALathon. And we're going to continue till this finishes. Well, I'm going to continue this till this finishes. I hope you've all taken lots of benefit. When we finish, over the next, I think today or tomorrow, there will be a questionnaire going out. So really appreciate if you can fill it in, if you watched it live or if you're watching the recordings, to help us to improve and just tell us what you think we did well and what we could do better next time. But thank you for those that have been watching live. It's always helpful to have people watching live, and also really appreciate everyone that's watched afterwards. It's always a shock because usually we've got around, particularly in the AQA sessions, we usually have maximum we've had is up to like 40-50 students watching live. In Edexcel we had a lot more initially, and it's kind of, I think it's between 10 and 20 usually, but as soon as the session finishes there's over 200-300 views, which means there's a lot of people watching but just not in sync with everyone else. If you're even 20 seconds out of sync, it's not classed as live. So really appreciate everyone that's been watching live, and everyone that's been watching out of sync as well, or just watching anyway, forwarding it, liking our videos, supporting us. Really, our team really appreciates all of that. If anyone's feeling a little bit sad that it's all coming to an end, don't worry. If you register yourself for the AMALathon 2, we'll be doing this all again in May. So a lot of what we're about to cover is stuff that we've already covered in chemistry, so I'm not going to spend too much time on this. We're just going to have a basic understanding and move on, or it's a quick recap. So the nucleus compared to the radius of the atom is about, the nucleus is about 1/10,000th of the atom size. Now, when you look at an atom, so for example, sodium, if you look at the periodic table, it'll look a little bit like this, which means it will have 11 protons, it will have 11 electrons, because that's the proton number at the bottom there, and mass number is one at the top. So, and how do you work out number of neutrons? You do top number take away bottom, so that's 12. Now, in an isotope, if you have, for example, carbon 14 and carbon 12, I'm going through this quickly because it's stuff that we've already covered. So in carbon 14, how many protons does carbon 14 have? It has 6 protons. How many protons does carbon 12 have? It's got 6 protons. So if we now work out the number of neutrons, carbon 14 has got 14 take away 6, which is 8 neutrons, and carbon 12 got 12 take away 6 is 6. So that means these are the same atom, they're the same element, they're both carbon. Why are they both carbon? Because they have the same number of protons. But why are they classed as isotopes? So the different versions of the same element, because they have a different number of neutrons. That's the definition of isotope. Same number of protons, different number of neutrons. Okay, the relative masses. So protons are 1, neutron is 1. Electron is, a proton is 1,836 times heavier than electron. So electron is 1/1836. So you can say very small, almost 0, but if you learn 1/1836 is better. Why are atoms neutral? Because they have the same number of protons and they have the same number of electrons. So let's look at carbon 12 as in our example. It has 6 protons. It's got 6 electrons. Protons are positive, electrons are negative. So the overall charge is 0. And this is why atoms are neutral. So we also already know that we have how many electrons in the first shell? 2, 8 in the second, 8 in the third. The majority of the atom's mass is in the nucleus in the middle, and the electrons are positioned in electron shells at specific distances from the nucleus. Now this is something that's really important for you to understand, which is when an electron gains energy, it goes up to a higher energy level. So when it gains energy, it goes up to a higher energy level. When that electron emits that energy, it goes back to that lower energy level. So when it gains energy, it goes to a higher energy level. When it releases that energy, emits it, it goes back to its original energy level. But what it emits is electromagnetic radiation. So it can emit gamma rays, for example. So this is what we covered in topic 5 yesterday. Okay, if an atom loses an electron, it becomes a positive ion. If it gains an electron, it becomes a negative ion. Okay, now we're on our new learning. So that's good. We covered that as quickly as I was hoping to, because it was just a recap. So what is radioactive decay? So radioactive decay is the process by which an unstable atomic nuclei loses energy or matter by emitting radiation, and that leads to stability. So an easy way to explain it would be this. You're at school, that's your desk, and your desk fits 4 people. So all 4 of you are sat there, and you've got your books open, plenty of space. Now a 5th person tries to squeeze in. There's a wall here, and you know what, the 5th person kind of can squeeze in. So the 5th person squeezes in. It's one of your friends. You want them to sit next to you. That's absolutely fine. Now, after that 5th person squeezes in, a 6th person tries to squeeze in. But this time when this 6th person squeezes in, there's no actual space for them. They've just kind of edged their way in. Now, what's going to happen now is it's going to be really uncomfortable, and you're all going to feel like you're about to fall out of your chair. And that's what's happening inside a radioactive atom, inside an unstable atomic nuclei. You've got so many additional neutrons inside there within that radioactive nuclei that the only way it can calm is if a small portion of it is emitted, or some energy is released. So here, either everyone can try and calm and stop pushing each other out and not move around as much, and that might help everyone just stay in the same place. Or if there's a lot of jostling and moving around, it could be that this person at the end falls out. Now, if that person at the end falls out, now there's enough space again for the 5. The instability has gone, and that's what happens inside a nuclear, an unstable atomic nuclei. So look, we've got uranium. If you compare the number of protons is the bottom number, neutrons is the top number. You can just see that it's got lots and lots of neutrons. So this is unstable. And how does it become stable? It releases, in this case, it releases an alpha particle, which is 2 protons and 2 neutrons. And then what we're left with is thorium, which is a little bit more stable than uranium is. So there's 3 types of radioactive decay. So radioactive decay is the process by which unstable atomic nuclei lose energy by emitting radiation. So they emit this radiation, and that could be alpha, beta positive, beta negative. So there's alpha, beta and gamma radiation. There's also neutrons, and from beta there's alpha and positive. So there's negative, beta negative and beta positive. So let me just repeat that: alpha, beta, gamma, and it can release neutrons also. And the category of beta decay, you can have positive beta decay or negative beta decay. We are going to cover both. So types of radiation: alpha, beta minus, beta plus, gamma, And this is maybe more for triple and neutrons. Neutrons can also be released. Now, background radiation. Now, background radiation is the radiation that's present in the environment all the time. And it comes from natural sources and from man-made sources. Now, from a natural perspective, it comes from cosmic rays from space. Now, those that did triple award space with me yesterday, topic 7, will understand this, that it's potentially rays that have come from the Big Bang. And then we've also got rocks. So things like uranium, it's a metal. All metals come out of rocks. We've just done reduction. Where did copper and all these other metals come from? They come out of rocks, from ores. So within these rocks, you can get small amounts of radioactive atoms that are decaying and releasing that radiation. And then you've got man-made sources, so fallout from nuclear weapons. So those countries that have dropped nuclear bombs, and also countries that have tested nuclear bombs or had nuclear accidents, for example, Chernobyl. Oh, thank you, Samina, for your feedback. I really appreciate it. I'm glad you've taken benefit from the sessions. So what can affect the radiation dose a person is exposed to? Occupation. So a person that's working with in radiography, working with x-rays, it could be location. So a person could be living in a place that just naturally has more radiation, or there's been, for example, what we mentioned here, a nuclear accident. Detecting radiation. So these are some key words here. We know what radioactive decay is. It's a process by which unstable atomic nuclei lose energy by emitting radiation, and that results in the transformation of an atom into a different element or isotope. So what we're saying here is that you've got your main atom, is what we showed on that initial first page. You've got, for example, uranium is unstable, but then it releases, for example, 2 protons and 2 neutrons, which are alpha particle, and then it ends up becoming a slightly smaller element, in this case thorium, which is more stable. Or you can release energy to become more stable as well. Then activity, the rate at which a sample of radioactive material decays or emits radiation. So this is how fast, this is how quickly, or how many nuclei are breaking apart like this, how many times this is happening per second. That's the activity. And count rate, there's machines that count how many decays are happening per unit of time. And how can we measure it? We can measure it using this, a Geiger-Müller counter. Now in an exam you can just write GM counter, GM tube. You don't need to remember Geiger-Müller. So Geiger-Müller tubes, so you can just remember it as Geiger-Müller tube, that's fine. They're used to detect and measure different types of radiation. So what are the different types of radiation? This is important. The question the most commonly asked about this. So let's quickly go through each one and look at, now there is a slide that summarizes everything, but we'll just go through each one anyway. So alpha particles can travel 3 to 5 centimeters in the air. They're the most ionizing. What that means is, because they're quite big and bulky, in fact what they're made up of is 2 protons and 2 neutrons. It's the nucleus of a helium atom. So if you took away the electrons from a helium, what you left in the central part, the nucleus, that's an alpha particle. So it's positively charged because it doesn't have electrons. Now it's quite a big chunky particle compared to the other radiation types, so it collides into air particles. So within 3 to 5 centimeters, boom, it's clashed into something and it's knocked one of its electrons away. So it clashes into something in the air, carbon dioxide, oxygen, anything, and it causes it to lose electrons. It's ionized it. It can be blocked by the skin or a thin sheet of paper. So before we showed the Geiger-Müller counter, if you had a piece of alpha particle and it was releasing alpha particles, if I put a piece of paper there, the alpha particle won't go past the piece of paper. So the count will go to 0. If I remove that paper, the Geiger-Müller counter will start showing me numbers again. Beta particles. Beta particles they do have a range of, it's more around the 1 meter. So you can travel about 1 meter in the air. They're less ionizing than alpha particles, but these ones can be stopped by a thin sheet of aluminium. So if I've got my Geiger-Müller counter, if I put a sheet of aluminium there, it'll block the beta particles. And beta particle is a high speed electron that's being emitted, because a proton changes into a neutron. So let me just explain this to you really quickly. What actually happens is, and this is showing you here, so let's say you got a neutron, it breaks up into a proton, and it breaks up into an electron. Now let's look at this really carefully. If I've got carbon 14 here, I have got neutrons, I've got 8. Protons, look at the bottom number. How many protons do I have? I have got 6. 6 protons. So what happens is one neutron turns into a proton and an electron. So now if one neutron turns into a proton, how many neutrons do I have now? I've just lost one, so I've got 7. How many protons do I have now? Because I've just gained a proton. The neutron's turned into a proton. So proton wise, I have got 7 as well. So now I've got a mass number of 14. And instead of atomic number of 6, I've now got atomic number of 7. So my carbon has turned into nitrogen. And it's also released a beta particle, or what we call an electron. So what are the different types of radiation? Now we're looking at gamma radiation. Now that can travel a massively long distance through the air. Why? Because think back to EM radiation, it's the movement of energy. And because it's the movement of energy, it doesn't have any particles. So the most penetrating form of radiation, meaning it can go really, really far. It can get through, so if I have my Geiger-Müller counter, it'll get through paper, it'll get through aluminium. What will block it, and to a certain amount, so it'll block more majority of it, but still some will go through, is either a thick layer of lead or an even thicker layer of concrete. And the gamma radiation can still go through, just slightly. It's a type of electromagnetic radiation. It has no charge, which means it's the least ionizing form of radiation. Okay, let's compare these radiations. Now, this is an exam style question which said complete the summary for the different types of radiation. So this is a really nice summary. So if you're memorizing, you can just pause on this slide afterwards and just memorize this. So alpha particle is made up of helium nucleus, which is 2 protons and 2 neutrons. It travels 3 to 5 centimeters in the air, but it's stopped by paper or skin. It is the most ionizing but the least penetrating. Then you've got beta particles. They're high speed electrons. They can travel up to around 1 meter in the air, and they're stopped by thin aluminium sheets. They are less ionizing. Then we've got gamma radiation, which is an EM radiation from the nucleus. It travels large distances and it's stopped by thick lead or concrete. It's the least ionizing. So memorize it, because questions come up on it. Don't lose marks. Again, I would advise, once we finish this, like I said, lots and lots of practice. Past papers. I can't reiterate enough from now till your exam how many past papers you need to do. The more you do, the more likely you are to get to a grade 9. If you do them all, then you've got a very good chance of grade 9, as long as you've understood. And for those that have been AMALing with me since Saturday, and they've been going through this, trying their best to go through the AMAL process, they will, I hope, get a grade 9. I'm looking forward to seeing results from those that have attended and watched the videos to see how much it actually has impacted. Because for years now, it's had a positive impact on my students. So I'm hoping it impacts students who aren't my students in school, but now become my students on YouTube. So how has the atomic model changed over time? Now this is something we've already covered, so I won't spend too much time on it. So Dalton, he thought they were just tiny spheres. Then J.J. Thomson discovered electrons and thought it was the plum pudding model, or don't write this in an exam, but more like a chocolate chip cookie model. Then the alpha part scattering experiment showed those that bounced back showed that they had a tiny heavy center, a nucleus. Lots and lots went straight through, which showed majority of the atom was empty space, and then some of them got deflected, which showed if the alpha particle was 2 protons and 2 neutrons, no electrons, meaning it had a 2 positive charge, then it showed that this nucleus must be positive. Oh, in H for some reason, positive. And then along came Niels Bohr, who then discovered electron shells and the fact that electrons orbit around the nucleus in fixed orbits at specific distances. And then came James Chadwick, who discovered and proved that neutrons exist in the nucleus. And this is the modern atom that we work with at the moment. Okay, beta decay. So we've got beta minus decay. Now we don't need to worry about antineutrinos. So let me just, that's probably the best one. Let's just get rid of that. All you need to know is that carbon 14 turns into nitrogen 14. Now I'm going to repeat this one more time. I did cover this, but just to make sure everyone's understood, it's carbon 14 it's got 6, actually I didn't even need to draw that, let me just erase that. We've got 6 protons and we've got 8 neutrons. So it's like saying this, we've got 1, 2, 3, 4, 5 and 6. Into the neutrons, we've got 1, 2, 3, 4, 5, 6, 7 and 8. Now what's happened is, during beta decay, a neutron transforms into a proton. So this neutron here has transformed into a proton. So now we have 7 protons and 7 neutrons. In other words, we have nitrogen. If it's got 6 protons, what is it? It's carbon. If it's got 7 protons, then it's nitrogen. And it's also released this fast moving electron. Now in beta positive decay, it's a little bit different. A proton changes into a neutron. So let's have a look at this. This is carbon 10. So we've got 6 protons, 1, 2, 3, 4, 5, 6. And we have to have 6 protons, otherwise it's not carbon anymore. But neutrons, we only have 4. Now this time, a proton, again, we don't need to know this antineutrino bit. This time, what's released is, this time a proton turns into a neutron and a positron. So a positron is a bit like an electron, but it has a positive charge. Now look, we've got 1, 2, 3, 4, 5 protons now. We've got 1, 2, 3, 4, 5 neutrons, sorry. So now there's no change in the mass number. We had 10 protons and neutrons before. We still got 10 protons and neutrons, but now we've got 5 protons, so we've got boron. So we need to understand nuclear equations. So we have to be able to write down what happens during radioactive decay, and you have to write down equations to show what's happening. That's an alpha particle, and that's a beta particle. Now, this is the change that you have to the nucleus. It changes the top number by 4 and the bottom number by 2. So in alpha decay, now this is not the alpha decay of radon, it's the alpha decay of uranium. So let's quickly go through this. Uranium, U. Now it's got a mass number of 235 and it's got a proton number of 92. Numbers have come out of place slightly. Now let's say a question says, and this is the kind of question you might get, and it might say it's released, this uranium has released alpha decay, and write a nuclear equation to represent it. So we know it has released alpha decay. Alpha decay is helium with a 4 at the top, 2 at the bottom. So it has released a helium nucleus. Now if it's released a mass number of 4, that means we're going to have to take 4 from 235. Take away 4 from 235, so that's now 231. It's released 2 protons, so the mass, because the atomic number is 2, so it's going to go from 92 to 90. So look, 92 equals 90 plus 2. And when anything with 90 protons is thorium, Th. That's all you've got to do for alpha decay. So look, now for beta decay, it looks like this. So we've got carbon 14 and 6. Now you might get carbon 14 and it might say it's released a beta decay, show the nuclear equation. So what you would do is this. You put the electron always looks like that. It's an E. It's got 0 at the top because it has no effect on mass number. Because 1 proton becomes 1 neutron, or 1 neutron becomes 1 proton, the mass number doesn't change because protons and neutrons both have a mass of 1. So if a neutron turns to a proton, it goes from 1, it still has the same mass. And for the atomic number, it has a -1 impact. So now 14 equals something plus 0, so that's 14. 6 equals something take away 1, so that's 7. What has 7 protons? Nitrogen. So we have now completed our beta decay equation. So these are just some practice questions for you to have a go at in your own time. Of course, obviously the answers are there, but you can still cover all the answers, as in from the arrow onwards, and have a go. So let's have a go at this one. Actually, it gives all the information as well. Complete the table comparing alpha and beta decay. So alpha particles emit a helium nucleus. That means the change in the mass of nucleus is it loses 4 units, and the charge of the nucleus, it loses 2 protons. So it loses 2 from the bottom number, 2 units. Now beta minus, it has no effect on the top to the mass number, but how does it change the nucleus? -1, it takes away 1 of the protons. Sorry, overall, not -1, it adds a proton. Activity. So what does this diagram show? It shows the activity of radioactive source reduces over time. and radioactive decay occurs randomly. So what does this graph show? Actually, one thing this does show is we've got around 16 nuclei there. We've got 8 here, 4 here, 2 here, 1 here. So the number of nuclei are halving. Now, in radioactivity, it generally takes the same amount of time for the activity to halve. And that's what this graph shows. So from this graph, you can work out how long it takes to halve, and that's what we call the half-life. So each radioactive isotope has a unique constant that determines how a nucleus will decay. As time passes, the activity of radioactive sources declines as the number of undecayed nuclei reduces. So initially you've got, for example, activity of 100. That means lots and lots of nuclei are breaking down, are unstable, and they're releasing radioactivity, releasing alpha, beta, or gamma particle radiation. Now, here, for example, it takes 1 day for it to halve. Then from 50 to 25, it takes another day. To go from 25 to 12 and a half, it takes another day. So by 3 days, within 3 days, whatever this particular radiation was, within 3 days, it had gone from 100, releasing as in 100 nuclei decaying, to 12 and a half nuclei decaying in 3 days. So the actual radioactive source, the activity of the radioactive source decays over time. The activity of the radioactive source declines over time. So what's the unit of activity? It's called a becquerel. So every time a radioactive material, a nuclei, decays, we call it 1 becquerel. Half-life. So half-life is the time required for the number of nuclei of an isotope in a sample to reduce by half. So here, for example, activity is 100. It means every second it's 100 nuclei decaying. So half-life means the time it takes to go from activity of 100 to activity of 50. Alternatively, it's the time it takes for a count rate from a sample containing the isotope to decrease by half. So we're looking at the count rate here. It's gone from 100 to 50. It took 1 day. Now to go from 50 to 25, it's gone from 1 day to 2 days. So it took 1 day as well. To go from 25 to 12.5, so it's halving again, it took 1 day. So here the half-life of whatever this radioactive material is, 1 day. So it's impossible to predict when a specific nucleus will decay, but half-life allows for the prediction of the activity of a large number of nuclei during radioactive decay. So how do you calculate half-life? So the substance here has a half-life of 1 day, and I've already explained how that worked. It had an activity of 100. To half that to 50, how long did it take? So 100 was here, 50, it was here. That was 1 day. Okay, 50, it took 1 day. To get to 25, it took another day. So that means every day it halves the activity. So it's the time taken for the activity to half. Now, determine the half-life for these different isotopes. So let's just quickly zoom in. So we can see these numbers just a little bit more clearly. So look, we had an activity of 600. And we want to know how long it took to get to an activity of 300. So let's go across and down. So I'd say that's about, this is in years I think, so I'd say that's about 2.7 years. Now here we've gone from an activity of 1000 to 500. So again we go down and we go across and down. So that is time in millions of years. This is for uranium. So that's around 4,500 million years. That's how long it takes for uranium to halve its number of nuclei. Hence it is very, very dangerous. Yep, 4,500. Now, what you can do beyond that to make sure it is actually that number. Sorry. Is from 300 to 150. If you go across and down, it's gone from 2.7 to 5.4. So that shows the half-life is roughly the same each time. Here, from 500 to 250, it takes it to 9,000. So that again shows the half-life is roughly the same. Okay, uses of radiation is triple award. And I'm going to come back to that in just a second, because 6.29 is combined. This is the last topic for combined, which is 6.29. So I'm just going to go through that with everyone, and then those people that are studying combined only will be able to finish and in a sense graduate from AMALathon 1. So, dangers of radiation. What are the hazards of radiation? So radioactive materials are hazardous. Nuclear radiation can ionize chemicals within the body, altering the way cells behave. This can lead to cancer. Radiation can also transfer large amounts of energy into the body, which damages and destroys cells. So when that radiation, particularly gamma radiation, it's highly penetrating, which means it can travel quite far without ionizing anything. But that means it can go through our skin, our bones, etc. It can get to inside of our body. And when it does do that, it means some of our internal cells can absorb the energy, and it can cause a breakdown of our DNA. So it can cause some of the hydrogen bonds in our DNA that attach. So if you think back to bases, what attaches one base to another or nucleotide to a nucleotide is weak hydrogen bonds. If those hydrogen bonds absorb the gamma radiation, it can cause the DNA to be damaged. And when the body then replaces that cell, it could lead to a mutation. So although ionizing radiation has the potential to cause cancer, it's also useful for imaging inside the body and for eliminating cancerous cells. So the energy that's in gamma radiation, it can also be used to destroy cells. And just to give you an example, this is more, and this is something that I did go through with students who did triple. So one of the things, let's say that's the brain. The brain is quite a sensitive organ. But if someone, I know no one ever has to go through this, but if someone's got a tumour at that part of the brain, cutting it out, messing around with it would be a problem. So what they would do is they would send radiation in lots of different directions, but make sure they all cross over at this point, meaning that one point where the tumour is gets most of the radiation. So that would cause that particular tumour to be destroyed without causing too much damage to the rest of the brain. Now, that's the end of 2.9. Okay, thank you very much everyone that's doing combined. Like I said, we really appreciate everyone that supported us and has been working with us all week, and those that are watching the recordings. We would have been happy if we had 10-20 people on every day, which is what we've had live, but we've been really overwhelmed with the fact that we've had over 2,000 views of all our AMALathon over the last 6 days. We've had about 300-400 views of each, 300 to 400 views of each AMALathon. The first one was over 1,000, so we really appreciate everyone that's shared, that's liked, and has subscribed. and that's been part of our AMALathon journey. So hopefully we will see you all, I'm talking to combined students here, I will hopefully see you all when we do AMALathon 2. If you haven't registered for AMALathon 2, if you look below, you can. And if you've not joined our WhatsApp channel, the WhatsApp channel is the best way to keep updated. If you subscribe and you're part of the WhatsApp channel, you'll get all the information, particularly for AMALathon 2. And on the WhatsApp channel afterwards, we will be putting a questionnaire. So if you are on the WhatsApp channel or your parents are on the WhatsApp channel, please give us some feedback. We'd love to hear something positive or constructive. Okay, thank you very much. Have a lovely evening. I hope your revision goes really, really well. If you have any questions, all you got to do is come to one of the AMALathon videos and just post your question. And as myself or someone from the team will answer it as soon as they can. So that's the same information for triple, because when I finish, I'm sure you guys will just want to go. I don't want to keep you hanging around for too long. Okay, 6.28. So I've got 6.28 to do, and then 6.30 till the end. So what uses do we have for nuclear radiation? So the management of or elimination of unwanted tissue. So what I've just explained with combined as well, it can be used to destroy cancerous tissue. The image demonstrates radiotherapy, where radiation is utilized to destroy cancerous cells. That's what I was just showing in just previously. The radiation must be used. The radiation used must have a half-life, but a short half-life. Not so short that it has no impact, and not so long that it just persists in the body, causing harm. So it should be sufficient to destroy the cells, but not so long a half-life that it causes additional harm. So we use nuclear radiation for smoke testers. Now the smoke detector functions by utilizing alpha radiation. A household smoke alarm detects the movement of alpha particles across a small gap. Now, what that means is inside here, you've got a small gap and you've got alpha particles moving across. So I don't think you can see that clearly. Inside there, you've got alpha particles, you've got a detector on this side, and you've got alpha particle source on the other side, and the alpha particle source moves across. If smoke enters the detector, and if you think back, the alpha particles are very ionizing. So as soon as smoke enters this area, it blocks the alpha particles going through, causing the detector to measure a decrease in the number of particles passing through the gap, and the alarm goes off. So the reduction in alpha particles causes the alarm to go off. Radiation is also used to irradiate food. So that means it's only on the surface of it, and it just kills off all the germs on the surface. You can use it, radiation is absorbed. You can use it also to change the thinness of aluminium, for example, or paper. But it's particularly using aluminium foil. When it's going through this machine, as you can see, that machine's got all these rollers and it flattens the aluminium out. Now you can use beta particles, or you can use radiation to change how thick you want the material to be. So radiation is absorbed as it travels through materials. This makes them useful for measuring the thickness of a material by assessing the amount of radiation that passes through. So imagine you've got a radioactive metal there. That means radiation will come down through the machine. Let me just change my color in this section here. Now, depending on how much goes through this material, they understand that will give an indication of how thick the material is. So this is frequently used with beta minus. So you have beta minus emitters here, and they're being emitted downward. Electrons are being emitted downwards. And it's used in industries such as paper milling and the manufacturing of aluminium foil. Now, if the foil is too thick, it absorbs more beta particles. So the detector receives fewer beta particles. This sends a signal to the rollers to apply more force to the foil, making it thinner. If the foil is too thin, That means too many beta particles go through. The detector receives more beta particles, so it sends a signal to the rollers to reduce the force, making it thicker. Now this is what I was explaining before. Examples include CT scans and the use of radioactive substances as tracers. No, actually, so I didn't explain this before. This is a little bit different, so I'm just going to explain it now. So, for example, you get hold of some radiation, and so you have medication that emits gamma radiation, and that will then flow through the person's blood vessels. Now, with the CT scan, it can detect the gamma radiation that's coming out of the body. So now if there's a blockage somewhere, it'll detect that blockage in the areas where the blockages are, and that means if it's a serious blockage, they can operate straight away. That means you don't have to, this reduces the need for exploratory operations. So in the past, they would have had to do an operation to see where the blockage was or what the problem was, and cut through the body and look for the problem. Now, it can just be done using a CT scan. So internal organs can be examined. And you've got the PET scan, which I covered again with triple ward already. It's the scans utilize a positron emitter as part of the process. These tracer materials such as fluorine-18 have very short half-lives and must be produced in the hospital and injected into the patient's bloodstream shortly after production. But they've got such short half-lives that have to be made there and then. So the emitted positrons interact with electrons in the patient's body, producing gamma rays, and that can be detected outside the body. So if you get a build-up of gamma rays in a certain area, that can indicate a problem. So multiple detectors can create an image of the movement of the tracers inside the body. So let's have a quick look at this exam style question. What are the advantages and disadvantages of using radiation as tracers? So the advantages are non-invasive imaging of internal organs. Disadvantage, the radiation exposure can be harmful. It provides real-time diagnostic results. But disadvantage, they're not connected, but it's a disadvantage. The short half-lives require local production. It aids in early detection of diseases like cancer, so it's a positive, but it requires careful handling and disposal of radioactive materials. At the end of the day, the hospital is then having to deal with radioactive materials, which is a problem. So what is advantages, disadvantages? Okay, we've gone through 6.29 already. Okay, 6.30. 6.30. So we have around half an hour left. Well, the end time is around 5:30, but if we need time longer than that, we will keep working. But we are too far from finishing the topic now. Guys are doing really, really well. Please keep asking questions if something doesn't make sense. Okay, how does the half-life of a substance affect its activity and associated risk? And what's the associated risk? So a radioactive isotopes have a broad range of half-life values. So they've got a broad range of half-life values. So depending on which one you use, some have got long half-lives, some have got short half-lives. For example, fluorine's got a very short half-life. Uranium has a short half-life of 4,500 million years. So if a substance has a short half-life, its activity decreases rapidly, which means if it's been put into someone's body, it reduces the risk of harm quickly. Now, from a safety perspective, we can manage the risk of radiation by storing radioactive sources in lead-lined boxes when not in use, wearing protective clothing, avoid in direct contact with bare skin, wearing face masks, monitoring exposure with badges. So there's something called a dosimeter, which is a badge that people who deal with radiation wear, and that absorbs the radiation and then it starts to indicate how much exposure they've had. And limit time, exposure time to radiation. So even someone that's working with x-rays all day, the second they press the button for the x-ray to occur, they always go behind the screen. So that just reduces their exposure. Okay, I should point out 6.31 and 6.32 are also combined. Never mind. Okay, so contamination and irradiation. Contamination is the unwanted presence of radioactive material on the surface of an object or within an object. But irradiation is the process of exposing an object or substance to radiation without direct contact with the radioactive source. So what are the differences? So one way to explain the difference would be this. If I've got a pencil and it's giving off radiation because there's something inside it that's radioactive, then that's contamination. It means it's radioactive material is physically transferred into or onto that object or person. Now when we say irradiation, a really good example for that is, for example, if you get when you have a surgeon, what they do with the surgical equipment is in a clear carrier plastic bag, you, for example, put a scalpel inside and you blast it with, that's supposed to be a scalpel by the way, you blast it with some gamma radiation. What the gamma radiation does, it kills all the germs, all the bacteria, anything that's in there that could cause infection, it kills everything. And it has a short half-life, so very quickly, all this on the surface, it very quickly stops being harmful. Now the next time that gets opened is just before the surgeon uses it in the operating theatre, which means it's very, 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 very clean. There's no germs in there, they're all dead. So when it occurs, contamination, when radioactive material is physically transferred to an object or person. Does the object become radioactive? Yes. If the object or person is contaminated with radioactive material, they will be radioactive. Stopping the radiation, you can only stop the radiation, it requires removing the radioactive material from the surface or from within that material. Now irradiation, the objects or the substance is exposed to the radiation temporarily, so it doesn't become radioactive because usually it has a short half-life, and the second and as soon as the exposure stops, because it's got a short half-life, very quickly or shortly after that, the radiation, because the half-life is so short, it stops becoming a risk. And stopping the radiation stops once the exposure ends, but the object remains unaffected. Okay, back to purely triple now. So everything now from 6.33 to 6.46 is now just triple award. So we're going to keep going till we're finished. Now if anyone feels like they need a break, just message me and say, can we have a break, and we will take a 5-minute break. Otherwise, we're going to continue till we're finished. So how can tumours be treated with radiation? So first we need to look at the type of radiation used and then the justification. So internally, they can use beta or alpha particles from isotopes like iridium-192. Why? Because the radiation can be applied directly to the tumour. So if they know where the tumour is, because they've done the CT scans or PT scans, they can take the iridium-192 and put it directly into that tumour. Now it'll start destroying all those cells within the tumour. Now it might harm some of the healthy cells around there a little bit, but it's 100% got rid of that tumour if it's put in the right place. And that minimises damage to the surrounding tissue. Now, the other type of radiation that we use externally would be gamma radiation from machines like a linear accelerator. That allows non-invasive treatment and targets a tumour from outside the body. Now, what that means is, when you use beta and alpha, you've got to put it inside the body. When you treat with gamma rays, you can treat from outside, meaning it's the example I gave before. If you're dealing with a tumour that's inside the brain, for example, the gamma radiation, they don't take a gamma radiation source and put it right in the middle there. They don't go, okay, let's put the gamma radiation there and it'll kill off everything. But with alpha and beta, they put it physically inside the human being. What they do with gamma is different. With gamma radiation, they release the gamma radiation from different angles. But if you can see here, what's happening when I'm going over with the highlighter, the area that gets exposed over and over again gets darker and darker. And that's what's happening with these scans. That region where the tumour is gets hit by the most gamma radiation, and it therefore kills, it destroys the cancer cells. And that means it allows a non-invasive treatment, so it means you don't have to cut into the body, and targets the tumour from outside the body. 6.34. What uses do we have for radioactive substances in medical diagnosis? So fluorine-18 is, as we mentioned already, it's really good because it's got a short half-life. It's used in PET scans by binding it to glucose. So they bind the fluorine to glucose. That then gets injected because glucose is soluble in water. It enters the bloodstream. So it flows through the bloodstream and it then accumulates near tumour cells. So you can see, unfortunately here, this area here, you can see that's accumulated there. So fluorine-18 emits positrons as it decays. When the positron collides with an electron, they annihilate each other. So when a positron and an electron collide, it releases a photon of light. When an electron and positron collide, it releases energy. Now, usually it can release a photon of light, but it can also release gamma radiation. It can release different types of radiation, but in this case, it's releasing gamma. And the gamma ray then is detected outside the body. Sensors that are placed around the patient's body detect these gamma rays. Okay, PET scans. So some of this is a recap for triple award, but that's good. The more times we go through something, the more importance our brain will attach to it. So sometimes the best way to learn is to teach someone. Still use the AMAL process, but when you're going through the activate phase, try teaching someone. When you're going through the past paper phase, do it with someone. Work with someone where you mark each other's answers and then give each other feedback. That process where you're helping the other person, it actually will end up helping you a lot more, because you have to process the information before explaining it. Now, fluorine-18 is used in PET scans because it's got a very short half-life. This means it must be produced nearby and used as quickly as possible. It decays too quickly for it to travel long distances, for it to be made anywhere else. Okay, we're now looking at nuclear power. What are the advantages and disadvantages of these non-renewable energy resources? So nuclear fuel, it's got high energy output, it's got no air pollution, and it's reliable energy. It's a reliable energy source. But disadvantage, it produces long-lived radioactive waste. There's a risk of nuclear accidents. It's expensive to build and maintain the power plants. So this is part of the reason why we don't have too many in the UK, because of the negatives. Having said that, it has the best, out of all the different nuclear radiations, it's amongst the best in terms of energy output. Now, what are the examples of nuclear reactions? So we've got fission. We've already spoke about radioactive decay. Now we're going to be looking at fission, and we're going to be looking at fusion. All of these are sources of energy. So when radioactive decay occurs, it releases energy. When fission occurs, although it doesn't show in this diagram, it releases gamma radiation. And when fusion occurs, it releases energy as well. And when I'm saying it releases gamma radiation, I mean energy, because gamma radiation is an electromagnetic wave, so it's the transfer of energy. So let's start with fission. Now you can see here, I'll put up the wording in a second. I'll just explain it in my own words first. What we've got here is let's use the example of uranium. That means it is an unstable nuclei. So not an atom, it's an unstable nuclei. So that's the protons and neutrons. Now for it to become stable, it can fission. Now usually when fission occurs is when a neutron from another radioactive decay, a neutron is released and it enters this nuclei, this one nucleus. Now the example I gave to you guys before, you've got 4 or 5 people sat at a table and that one extra one sits and another one sits, another one sits. Eventually there's one person that sits that causes so much instability that one person falls out, and that's what's happened here. That neutron has caused an instability within that nucleus, and it causes it to fission. So it breaks apart into 2 smaller nuclei and it releases neutrons. So it releases 2 or 3 neutrons. Now, when those neutrons are absorbed by another uranium nucleus, they also become even more unstable and do the same thing, release 3 neutrons and break into smaller fission products. Now we've got 9 neutrons being released. So they will have an impact on 9 more nuclei. So 27 neutrons will be released. So it's exponential. And all this is at the same time releasing lots and lots of energy. So that's why we use it in nuclear power plants. So once you've got the fuel releasing lots and lots of neutrons, you're releasing lots and lots of energy. And that energy can then be used and converted into electrical energy. So nuclear fission involves the division of a large and unstable atomic nucleus. So here's our unstable and large atomic nucleus. Spontaneous fission is uncommon. So nuclei don't just suddenly start releasing neutrons, but once they do, then fission starts to take place. The unstable nucleus typically needs to absorb a neutron first. So once one of them has gone through random decay, spontaneous fission, as in one of them has just spontaneously released a neutron, it then has a knock-on effect on the next nuclei, which has a knock-on effect on 3 nuclei because it's released 2 or 3 neutrons, which has a knock-on effect on 9 more nuclei because each one of those 3 nuclei has released 3 each, 2 or 3 each. So the nucleus that undergoes fission, it typically breaks into 2 smaller nuclei that are approximately of equal size. So it splits in half. Along with this fission process, 2 or 3 neutrons and gamma radiation are released. So that means the fission reaction produces energy. It's that energy that's harnessed in a nuclear power station. So all products of fission carry kinetic energy. The neutrons that are released, they trigger further chemical reactions. So we can use that in a nuclear reactor. So in a nuclear reactor, a neutron is absorbed by uranium-235 nucleus, turning it into unstable uranium-236. The nucleus then splits into smaller nuclei and releases 2 or 3 neutrons. So there's our uranium, it's just released 2 or 3 neutrons. So that's supposed to be an N. These neutrons trigger more reactions, creating a chain reaction. So now that neutron is absorbed by the next nuclei, then that releases 3 neutrons. And the next one releases 3 neutrons, the next one releases 3 neutrons. So it becomes more and more and more, so it's exponential. So inside the reactor, so you can see here, you've got these control rods, and in between control rods, so if you've got fuel rods, and in between the fuel rods you've got control rods. Now the control rods usually stay up, but if the fuel starts releasing too much energy, then the control rods are brought down, and the control rods absorb some of the neutrons, and they absorb the energy just to calm the reaction down. So the fast moving neutrons carry the majority of the energy from the reaction. The neutrons must be slowed down before they collide with the new uranium nuclei. This transfers energy to heat water, so the water turns to steam, that spins the turbines, and that drives the generators generating electricity. So the energy is used to boil water. The water then turns steam turbines, so it works in a similar manner as like a windmill. The windmill makes the turbine spin, and that generates electricity. When we use coal, we burn the coal, we boil water, the steam makes turbines spin, it generates electricity. Same thing here. The energy that's coming out of the reaction, we're using it to heat up water and release. The energy that's released, it heats up water and turns to steam. The steam turns a turbine. So the nuclear split when struck by an. So the nucleus from the nuclear fuel splits when it's struck by an incoming neutron. But that's something we've already explained. So what do the different parts of a nuclear power station actually do? The graphite core slows down neutrons, increasing the chances they will be absorbed by the fuel rods. If they're not absorbed by the fuel rods, then it won't have that chain reaction effect. So these control rods are positioned beside the fuel rods, and that just slows them down if they're going too fast. That also keeps the reaction calm, as it is, doesn't allow it to exponentially increase too much, so it keeps it set at a certain level. So at certain times the control rods will move up and out of the way to speed things up, at certain times they're being brought down to slow things down, so that it doesn't become we don't end up with a nuclear disaster. Because if it was left to just exponentially keep increasing, the energy levels would increase and increase and increase, and that could cause a meltdown or cause a nuclear power station to stop working, or it would be explosive. What do different parts of a nuclear power station do? So the control rods, they absorb neutrons, preventing them from moving between fuel rods. This allows them to regulate the speed of the chain reaction. So that regulation is important to stop any disasters from happening. By raising and lowering the control rods, we can adjust the speed of the chain reaction. And what do different parts? So the water is heated to produce steam, which drives the turbines in the power station. The coolant absorbs the energy released from the fission reactions. So the coolant is used to absorb the energy. Okay, and what are the products of fission? So the byproducts of nuclear fission are radioactive as well. As a result, nuclear power stations generate nuclear waste. Okay, fusion. Nuclear fusion occurs when two light nuclei combine to form a heavier nucleus. So that usually means, to explain it really simplistically, it means the nucleus of a hydrogen plus the nucleus of a hydrogen becomes helium. There's more steps to it than that, but when we say nucleus, because nuclear fusion happens inside stars. Now, if you think back to what we were saying before in electromagnetism and also today, if you have an electron, if it gets excited and increases in energy, it goes to a higher energy level. So if you can imagine the amount of energy that we have inside the sun would cause all the electrons to separate and delocalize and deseparate. So in the sun you won't have an atom, especially these smaller atoms. You don't have atoms. What you have is just the nucleus, because the electrons have become so excited they've separated from the nucleus. there's no longer electron shells. So during this process, so nuclear fusion occurs when two light nuclei combine to form a heavier nucleus. And like we mentioned yesterday, because this was a topic in the topic of space as well, the heavy ones, things heavier than iron, the research leads to the assumption that the ones heavier than iron, the atoms heavier than iron, are produced during supernovas. Now during this process, some of the mass is converted into radiation energy. So it leads to radiation. Fusion provides the energy for stars. So here you've got deuterium, that's a proton and a neutron. So these are heavy hydrogen. And that's a proton with two neutrons. So these are isotopes of hydrogen. And when you get two of those isotopes and they are fused together, and think back to what we learned yesterday, what does the sun have that would cause them to fuse together in the first place? And that is a really strong gravity. Otherwise those protons will repel. The only thing that's overcoming that repulsion is the gravity of the star, which then leads to two protons and three neutrons. One neutron is released and we're left with a helium nucleus, which is mass number of 4 and 2 protons. And there's a lot of energy released by this, a lot of energy. So let's compare fission and fusion. Fission is the splitting of a large nucleus. Fusion is the joining of two light nuclei. Energy released. Fission, a large amount of energy is released from the splitting, but fusion is a huge amount of energy from the combining. In fact, fusion needs a lot of energy for it to even happen. Radioactivity of products. The product from fission is radioactive, but the product from fusion is not generally radioactive. At a certain point, when you get heavier and heavier elements, then yes, it could potentially be radioactive, yes. And energy needed for the process to occur. Fission needs a neutron to start, so not too much energy. But fusion requires high temperature and pressure, hence it happens inside stars. And it's once fusion starts, is what we said yesterday, gravity is pulling inwards, but what's pushing back outwards to maintain the shape of the star is the fusion reaction, and that then maintains the size of the star. Now, for fusion to occur, fusion occurs only at high temperatures and pressures. So it's understandable that it can only happen, or it properly happens within a star, because a star's got the gravitational field that overcomes the proton's natural kind of what naturally would happen between protons, which is they would repel. So the gravity, so why do we need high temperatures and pressures? Because protons repel each other electrostatically. The positive charges push each other away, but the gravity of the sun overcomes that. What are the conditions for nuclear fusion to take place? High temperatures and pressures make fusion reactors difficult and expensive to build. So this is something that they've tried on Earth. Fusion requires temperatures between 100 and 200 million degrees at low pressures. So the pressure on Earth is quite low. So you consider the gravity of Earth compared to the gravity of the sun, it means we've got to compensate with an increase in temperature. Now fusion has been achieved on Earth, but it's not yet financially feasible. And that is the end of AMALathon 1 2025, the Edexcel section. So that's the end of the Edexcel Edexcel AMALathon 2025. So I hope I'll see you all at the AMALathon 2. I hope you've more than enjoyed. I hope you've taken benefit from the sessions, I am sorry that we didn't get to do topic 5 chemistry, but like I said, if you have any questions, I know it's the ones who are live, it's the triple award students that I've had lots and lots of triple award students that have been live every single day. I really appreciate that you've taken the time and you've put that effort into it. I hope you guys do amazing in your GCSEs. Like I said, if you have any questions, go straight to the AMALathon videos and just post the question. I'll do my best to answer it, or someone from the team will do their best to answer it as soon as they can. Right guys, have a wonderful holiday and I hope your revision goes really well.